the incredible and mysterious universe. It's boundless, enigmatic, and in many ways, even intimidating. At the same time, its grandeur and wonder are unlike anything else we know. It's the cradle of all existence, our point of origin, and a place we'll always strive to explore. Yet, the universe is filled with mysteries and unexplored phenomena. In this video, we'll embark on a thrilling journey through the most mind-blowing mysteries of our universe. We'll learn why no one has solved the Fermi paradox and whether we are truly alone in the universe. Why has no one heard us, and why haven't we heard anyone else so far? We'll explore the immeasurable depths of the universe, trying to understand where it ends and what lies beyond its edge. We'll unravel the mystery of vast cosmic voids, where there is nothing for millions of light years around, as if time stood still inside them. We'll uncover the first evidence suggesting the existence of the multiverse. We'll dive into the simulation hypothesis and examine the evidence suggesting that we live in a programmed world controlled by an unknown entity or artificial intelligence. We'll venture into the realm of dark matter and energy to understand how they shape the way we perceive the universe. We'll examine a mysterious star and ponder why some people believe it's a nuclear waste dump. We'll research temporal paradoxes and find out if it's feasible to time travel. We'll discuss the enigma of the wow signal received from the depths of the universe and analyze the first interstellar object speculated to be remnants of a crashed spaceship from an ancient extraterrestrial civilization. And finally, we'll wonder what will happen after our universe dies, and how vast will its new mysteries be. Mysteries of space. Your likes improve this video's ranking and help YouTube algorithms identify it as interesting. Kindly show your support. There are at least 100 billion stars in our galaxy, the Milky Way. There are about 2 trillion large and small galaxies in the visible universe, approximately 200 billion trillion stars. Just take a moment to appreciate this number. And that's considering only stars. But we already know for sure that stars have planets, and in most cases, more than one. And when somebody poses the endless question, are we alone in the universe? It's somehow strange to hear the unequivocal, yes, we are alone. Indeed, among the thousands of confirmed exoplanets, there are plenty of Earth-like planets. You don't really suppose that such an unimaginably gigantic number of planets in the observable space is uninhabitable? Or maybe it is. In fact, not everyone could appreciate the importance and the profoundness of this natural science question. And today, we'll get some answers to this question. Buckle up, you're in for a treat. Some of what you will hear and realize may stun or even frighten you. In this video, you'll learn why finding fossils of a very complex form on another planet would be the worst news ever to make headlines. Can we be part of a space reserve? Or maybe we are just a character in some supercomputer? Stay with us to find out. Some of the facts may really shock you. The Fermi paradox and the great silence of the universe. Subscribe to the channel and like this video. It all started with a famous small talk over dinner. Unfortunately, this conversation became known only through third parties. They say that one day in 1950, physicists Emil Konopinski, Edward Teller, Herbert York, and Enrico Fermi himself, an American physicist of Italian origin, one of the creators of the world's first nuclear reactor, met at the university for lunch. Konopinski recalled that they first discussed numerous eyewitness accounts of UFOs, which was a very popular topic in the 1950s. Gradually, the conversation turned to the question of whether material objects can move faster than the speed of light, and Fermi made everyone laugh with a rhetorical question. Then where is everyone? But really, where is everyone? Why haven't extraterrestrial civilizations contacted us yet? With our television and radio programs, we've been sending signals into space for about 100 years. We've also deliberately sent into space naive but daring signals for extraterrestrial civilizations. What's more, we've connected thousands of space enthusiasts on the internet to recognize signals received by the Arecibo Observatory in Puerto Rico as a part of the legendary SETI program. Still nothing. Only silence. However, according to Herbert York, Fermi then performed more scientific calculations, multiplying the probabilities of the existence of Earth-like planets, the emergence of life on them, the development of intelligent life forms, and so on. As a result, he concluded that aliens should have visited the Earth a long time ago, and more than once. York says that Fermi made several suggestions at the time to explain why this didn't happen. According to him, either interstellar flights are impossible, or they are not worth the effort, or technologically advanced civilizations don't live long. But Fermi didn't know about wormholes at the time. And if he knew, he would probably say that everyone already had a wormhole in their apartment with a pair of curious alien eyes intently watching us, or some other sense organs they had. Perhaps the Big Brother has been watching us all along. And he's damn right. Just think about it. Scientists are already seriously considering the possibility of wormholes. And we just need to advance our technology a bit more to learn how to create them. But then again, the question arises, where are they all? One way or another, according to Herbert York, Fermi's conclusions anticipated the no less famous Drake equation. The subsequent long-term debate about alien civilizations and the eternal question of, where are they after all? 10 years after Fermi's ideas, Dr. Frank Donald Drake, professor of astronomy and astrophysics at the University of California at Santa Cruz, decided to comprehensively tackle this question. He came up with his famous equation designed to determine the number of extraterrestrial civilizations in the galaxy humanity has had a chance to contact. This probability was obtained by multiplying the star formation rate, the proportion of stars with planets, the probability of the emergence of intelligent life on the planets, and so on. In total, there were 7 parameters. Of course, we're far from knowing most of these parameters. But Drake didn't formulate the equation to solve it, but merely to keep the dialogue alive. And he really managed to do it. Over the past 70 years, there have been many hypotheses and theories supporting the Fermi paradox and its reflection in the form of the Drake equation. So, hello, where is everyone? Why can't we hear anyone? And why isn't anyone hearing us? One of the most debatable theories is that of the Great Filter, outlined by Robin D. Henson of the Future of Humanity Institute at Oxford University. This is a kind of hypothetical barrier that can be set for humanity either in the past or in the future. The hypothesis concludes that the easier human evolution has been so far, the worse destiny we might have in the future. Doesn't sound obvious? Do you remember this joke? I intend to live forever. So far, so good. Well, it seems that we can easily apply it to all humanity, not just individual human life. Not so funny anymore, is it? When trying to understand why we don't see evidence of aliens, Henson questioned the high estimated possibility of the existence of technologically advanced extraterrestrial civilizations. Some unknown factors can reduce the likelihood of the emergence and development of life forms to the point where traces of their activity can be registered by others. In part, it is precisely for this reason that the average lifetime of a civilization may turn out to be too short for it to intersect with another one within the same historical epoch and reachable region of space. This can be compared to the ripples in the water created by the thrown stones. If you only occasionally throw pebbles in the water, the ripples will easily get lost in the entirety of the pond. The analogy is obvious considering the scale of space and civilizations. While one civilization is still learning to use fire and the wheel, the other has already died in a nuclear war, or for any other reason. In the vast space of billions of parsecs and over billions of years, the chances for civilizations to miss each other are much higher than for ripples on the water in some pond. Isn't that true? Just think about history and how many times humanity has already been on the brink of destruction. But why say has been? We don't have to look very far. Do you remember the year 2020? The pandemic reminded us that our entire civilization may only be a short glimpse in the history of the Earth. But let's go back to the scientific approach. Henson estimated the evolutionary stages needed for the emergence of an interstellar civilization. 1. The formation of a star system with planets suitable for life. 2. The emergence of replicable molecules, such as RNA on one of the planets. 3. The rise of simple single-celled life forms, prokaryotes. 4. The development of complex single-celled life forms, eukaryotes. 5. The emergence of sexual reproduction. 6. The evolution of multicellular organisms. 7. Developing intelligence capable of using tools. 8. A civilization becoming advanced enough to colonize space. We've reached this level. 9. The spread of civilization through space colonization. According to the Great Filter hypothesis, at least one of these stages is extremely unlikely. If steps 1 through 8 are highly probable, then a lot of civilizations in the universe would have evolved to the current level of humanity. However, none of them seem to have made it to step 9. Otherwise, the Milky Way would already be full of colonies. So step 9 might be improbable. And anything can prevent us from taking this step. A nuclear war, an epidemic, an asteroid, depletion of resources, underestimating some social processes, or anything else. Some very unexpected and discouraging implications may follow from these slightly confusing considerations. But let's indulge in some science fiction and imagine that we did find traces of life on the nearest planets. First, this would suggest that life can independently emerge on different planets, and it's an extremely common phenomenon. If we found the simplest life forms in Martian soil or under the ice of Jupiter's moon Europa, this would mean that the Great Filter should be set somewhere after this period of evolution. This would have been slightly unsettling, but we could still hope that the Great Filter is in our past and that we have already passed it. If we were to discover a more advanced life form, such as some kind of multicellular organism, that would remove many more potential Great Filter periods from the universal timeline of any life form. And the chance that the Great Filter is in our future and not the past would increase significantly. But if we discovered the fossils of some very complex life form, for example, a vertebrate-like creature, then this discovery would be both sensational and equally tragic. In this case, we would consider that the Great Filter is still ahead of us. Such a discovery would be a devastating blow. As Nick Bostrom said, that would be the worst news to ever make the headlines. Why? After all, such a find can suggest that life is indeed very widespread. But that's good. It's good, isn't it? But judging by the Great Silence, not a single civilization in billions of years has been able to break through the Great Filter. Do we have a reason to believe that we'll be the first? Once again, imagine that we started finding traces of extraterrestrial life everywhere. Yippee! But there is one but. We only find traces, and there's no evidence of living, let alone advanced civilizations. How does it feel to receive indisputable evidence of the existence of complex life forms in the universe and at the same time realize that we were never destined to contact them? Moreover, as a civilization, we are most likely doomed because of the inevitable Great Filter, whose nature we don't even understand yet. Now, don't you feel relieved when you realize that it's nothing more than a hypothesis? But it's our human nature that makes us see the future with great optimism and ingenuity. And it was human ingenuity that helped many scientists and intellectuals to come up with alternative theories on what caused the Great Silence. However bizarre, many of these theories became widely discussed. Let's consider some exotic hypotheses. In order to understand them, we will need to temporarily disable our common sense. And there is nothing unscientific about that. After all, by and large, common sense is only the sum of the preconceptions of its time. Several centuries ago, Giordano Bruno wasn't driven by common sense. By the standards of that time, his executioners were the most sensible ones. This is the least extravagant of the exotic hypotheses, but this theory can instill the feeling of worry and dismay. Chinese science fiction writer Liu Cixin proposed the concept of a dark forest to explain the Fermi paradox. In short, it poses that the evolution of life in the universe implies continuous competition and survival of the fittest among advanced civilizations. Therefore, any sufficiently developed civilization carefully hides the evidence of its existence to avoid being attacked by competitors. The young civilizations that give this evidence away are like inexperienced travelers walking through a dark forest. He might think that there's no one around, but if he makes enough noise, sooner or later he will run into a predator. And alas, the traveler is dead before he knows it. We can clearly see how it aligns with Stephen Hawking's ideas. Back in the day, he voiced some concerns about sending signals into space for hypothetical distant civilizations. Hawking argued that such actions are too naive and reckless, and if someone finds us thanks to such efforts, it may end badly for us. The history of South American civilizations clearly proves this point. But what if more advanced civilizations have long discovered us, but turned out to be far less aggressive than Hawking imagined? The next idea might sound totally crazy. This is the Serengeti National Park in Tanzania, the oldest nature reserve in Africa. It's one of the most famous and largest national parks in the world. It is considered to be one of the most complete ecosystems on the planet. Its area is almost 15,000 square kilometers. It is home to 3 million large animals and almost 500 species of birds. The Serengeti is also famous for the natural migrations of hundreds of thousands of wildebeest, gazelles, and zebras. During the migration, animals cover 3,000 kilometers. Although the Serengeti attracts tens of thousands of tourists every year, most of the local higher animals have never seen people. Not to mention those who established this national park and set restrictions for visitors. Ironically, it's quite fitting to consider them the creators of this isolated world. These animals don't even know that they live in a large nature reserve. They are not aware of any boundaries, rules, and the creators themselves. For them, human civilization doesn't exist. And if they were smart enough, they too would wonder, where is everyone? As for the lower animals, the trope of a nature park is redundant. To an ant or a butterfly, humans don't seem like a large or threatening species, but an incomprehensible phenomenon of nature, like rain, wind, sunlight, winter, or summer. What if somebody considers our world nothing more than a nature reserve? And by our world, we mean not just Earth, but the whole universe. And we simply can't recognize those unknown powerful creators with our senses or comprehend them with our minds. Sounds too incredible? But that's not all. There are even more bizarre hypotheses. Here we are, balancing on the edge of science. But we can't help but mention this hypothesis, at least for one reason. Its author is Nick Bostrom, a Swedish philosopher and professor at Oxford University, known for his work on the anthropic principle. His article, Proof of Simulation, is considered to be the main work in this field. It was published in 2003 in the Philosophical Quarterly. Bostrom's main idea is that if we don't think that we are currently living in a computer simulation, we are not entitled to believe that we will have descendants who will run lots of simulations of their forebearers. In short, the main idea is as follows. Over the course of its development, technological civilization creates more advanced computer simulations. If we go a step further, we see that individual simulations become so complex that their inhabitants begin to create their own simulations, and so on. With some reservations, let's give credit to this theory, especially given the fact that our civilization actually does this and succeeds in creating more and more complex and realistic simulations. Computer games become shockingly lifelike. And if we assume that we are in one of these simulations, then the great silence of space is just the rules of the game, the initial conditions, period. There are many exotic hypotheses like these explaining the great silence, and we haven't even mentioned here the most ridiculous ones. Surprisingly, all of them may turn out to be much more likely than the answer that is literally in front of our eyes. The most obvious one, the one that follows directly from the Great Silence. It's so unnervingly straightforward that we don't even want to say it out loud. What if we are really alone? And this answer sums up one of the most convincing theories that explain the Great Silence and the Fermi paradox. But at the same time, it's the scariest and most frightening one, because it takes away our last hope. If you've been following this topic for some time, you're probably well familiar with an ironically unambiguous statement that the Earth is just another rocky planet in a regular planetary system near an inconspicuous star on the outskirts of one of the countless trillions of galaxies. Ironically, this idea wasn't proposed by hype-seeking tabloid journalists. It was along the lines of what Carl Sagan and Frank Drake said. Just like many other scientists, they believed that given our planet's unremarkableness, the universe could well be teeming with life. This point of view even has a distinctive name, the mediocrity principle. And yet again, we find ourselves wondering, where is everyone? Actually, everything is much more complicated than it seems. Thanks to some researchers, the principle of mediocrity found its way into the scientific pop discourse and didn't raise any objections until a few years after. You see, there wasn't much discussion on this subject, although there should have been more. But the discoveries of recent years still forced us to question the mediocrity principle after all. But if this principle is a bit frustrating, its alternative is much worse. It instills a sense of total loneliness, existential despair, and hopelessness. We may be the result of such a fortunate coincidence that it could be simply described as one in the whole universe. This idea has developed into a fairly consistent rare Earth hypothesis. Peter D. Ward and Donald Brownlee's work, Rare Earth: Why Complex Life is Uncommon in the Universe, dives deeply into this issue. In the book, they make a compelling argument for why the emergence of complex life is an unimaginably rare or even unique phenomenon requiring exceptional astrophysical and geological coincidences. According to this hypothesis, a planetary system capable of supporting complex life should structurally resemble the solar system, and the slightest variation may ruin everything. Many people believe the so-called Goldilocks zone or habitable zone is virtually the only condition life needs to emerge. The Goldilocks zone is a region around the star where conditions on the planet's surface orbiting the star will ensure the existence of liquid water. In our case, the uniqueness also lies in the fact that the Earth's orbit is quite round, and we never find ourselves too far from or too close to the Sun during the year. And that's just the beginning. As we go deeper into the question, we'll find more and more conditions. Not everyone knows, but not only stellar systems have a Goldilocks zone. The Earth is lucky enough to be in such an optimal zone in our galaxy. That might not be the most obvious idea, so let's go into detail. It takes about 235 million years for our system to orbit the center of the Milky Way. That means, since the oceans appeared, our planet, together with the Sun, has covered all this distance 17 times. It has done it 15 times since the appearance of the first actual traces of life, and 7 times since the rise of the first multicellular organisms. By the way, this hasn't been an easy flight. You can only loosely consider this distance complete emptiness in intergalactic space. A lot of unpleasant surprises may await our tiny solar system on its way through the galaxy. They can be fatal for the whole system, not to mention our planet. What's more, a dead zone constitutes the most part of every galaxy, the Milky Way included. This zone can't support complex life or give rise to any life at all. Why is that? The closer to the center of the galaxy, the stronger the destructive effect of X-ray and powerful gamma radiation emitted by the neutron stars and black holes with their jets. As you approach the galaxy's center, you'd see more and more of these monsters. And the closer you are to the center, the closer the supernova flashes. And these are weapons of mass destruction, capable of destroying entire worlds from many light years away. In addition, proximity to the center makes gravitational disasters more likely. Even if a planetary system had optimal parameters, it would take one close flyby of a star, or worse, a black hole, to mess up the whole thing. At this point, we already can see that basic mathematics doesn't work. Statements like, there are hundreds of billions of stars in the galaxy and even more planets, which means the galaxy should be full of life, are fundamentally wrong. The thing is that most stars lie close to the galaxy's center, which is packed with heavy action. Even if life emerges here, it won't last long. At the same time, being too far from the center of the galaxy is also bad. The farther from the center, the lower the star's metallicity, which is one of the key factors for the formation of Earth-like planets. Recent research suggests that the length of the galactic habitable zone is from 7 to 9 kiloparsecs. This is approximately 22.8 to 29.3 million light-years away from the center of the galaxy. Surprisingly, on average, no more than 10% of stars fall into this zone in the Milky Way galaxy, and that's taking into account the most optimistic estimates. However, time is the most critical factor. For billions of years, the planetary system should have suitable conditions for the origin and, most importantly, the maintenance of life. Therefore, the planetary system should preferably have an ideal orbit around the galaxy's center, so as not to fall out of the habitable zone even for a short period. And lo and behold, the solar system lies exactly in the habitable zone of the whole galaxy, and its orbit is almost perfectly circular. But wait, there's more to it. Our entire galaxy is a pretty rare phenomenon. 10 billion. 10 billion years. This is about how long the Milky Way hasn't collided with other galaxies. Let us remind you that the age of the entire universe is just over 13 billion years. This is part of the reason why our galaxy is a fairly quiet place, a safe haven if you will. On average, there are only 7% of such galaxies in the universe. And now let's remind ourselves that our galaxy is currently moving pretty fast towards its closest neighbor, the Andromeda Galaxy, and they will almost certainly collide. Perhaps this will be the great filter for our civilization. However, this won't happen for at least 4 billion years, but still. Although if humanity proves to be so inept that it can't venture into deep space in 4 billion years, then it's doomed anyway, for many reasons. Let's go to our next point. When gazing at those brilliant dots scattered across the night sky, we sometimes think that any of them might look something like our sun, except for different sizes and luminosity. But that's far from the truth. According to various estimates, about half of all stars in our galaxy constitute at least binary star systems. Take, for example, the North Star. The fact is, there are as many as 3 stars there, locked in a space dance with unpredictable trajectories. In sci-fi films, we have often seen a colorful landscape with the sunset or sunrise of 2 or 3 suns on a faraway planet in a faraway galaxy. However, there are a bunch of reasons why planets in such systems would most certainly not become a cradle of life. First and foremost, it's highly unlikely that these planets would have a stable orbit for billions of years. Not to mention, the issue of the habitable zone becomes much more complicated. But there's no need to go that far. Despite its seeming mediocrity, the Sun has extremely rare characteristics. Our star is surprisingly stable and has a luminosity variation of just 0.1%. And even though many stars have been discovered that belong to the same class as the Sun, not a single one is known to have a similar mass, luminosity, age, temperature, and metallicity. And each of these factors plays a crucial role in the big equation that determines whether or not life is possible. There are a lot of issues like this, and we could discuss them for a long time. They include the strange structure of our solar system, the uncharacteristic location of gas giants, the fortunate presence of the moon, which stabilizes the Earth's axis, and much more. But even if you take all these low probabilities combined, none of them come close to the barrier that really shifts our ideas on what's possible and what's not. We are talking about the origin of life and evolution as we know it. Even if we make things easier and accept the panspermia hypothesis, which suggests that life came to Earth on a comet, the paradoxes of further evolution are unexplainable. Life on the planet survived 2 great glaciations that took place 2.2 billion and 635 million years ago. And who would have thought that these 2 seemingly cataclysmic events facilitated the evolution of life? The first stimulated the development of photosynthetic microorganisms, which greatly reduced the concentration of greenhouse gases and triggered the accumulation of oxygen. And following the second glaciation, the legendary Cambrian explosion occurred that gave rise to almost all existing evolutionary branches. As a result, the first brain appeared. Let's make a small digression for the sake of a complete picture. Such a dramatic and complicated history with several glaciations and mass extinctions contributed to the evolution of life forms and their complexity. If we found a hypothetical paradise planet with ideal conditions, most likely it wouldn't host life, or it would be too simplistic. There are no complex tasks to solve that require a lot of effort. There is no need to complicate things and evolve in paradise-like conditions. If things around you were super easy, why would you evolve into something more advanced than yeast? Therefore, no matter how cruel it may sound, contrasting conditions are absolutely needed for evolution. Favorable factors aren't enough. They should be balanced with unfavorable ones. Winter, summer, day, night, predator, prey, life, death. However unpleasant this may sound, it is an academic fact, and evolution itself proves this conclusion. This being said, the unfavorable factors shouldn't be too extreme, because life is still a rather fragile thing. How many factors should align in this kaleidoscope of probabilities to create a chain of events leading from a lifeless planet to a technologically advanced civilization capable of conquering space? Please keep in mind that we are making an assumption about panspermia, that life on Earth arrived already ready-made. But if we want to be completely honest with ourselves, we'd have to leave this assumption behind. After all, life had to emerge somewhere, somehow. Suppose there was a place in the universe where all of the above unlikely favorable factors came together. All habitable zones, the perfect combination of the star's parameters, a rocky planet, the presence of a large satellite, water and atmosphere, and so on and so forth. A completely identical twin of the Earth somewhere in deep space. So what's next? Nothing. The very first brick that modern science considers life is the replicator. That is, a complex molecule capable of self-replication. It is only with the emergence of the first replicator that evolution mechanisms start to operate. But the first replicator itself must have come about by chance. And the problem is that even the simplest replicator is still too complex for it to appear entirely by chance. Scientists have run countless sophisticated computer simulations on this topic, and the results have given us more questions than answers. A recognized international expert in evolutionary and computational biology, Russian-American scientist Eugene Koonin calculated the probability of the spontaneous appearance of the first replicator. He argues that the number is 1 times 10 to the power of 1018. That is 10 with 1018 zeros. Just so you know, the number of atoms in the universe is 10 to the 80th power. This is 0 compared to 10 to the power of 1018. It is essentially impossible to comprehend this ratio. Even such a prominent scientist as Eugene Koonin had to take up the multiverse hypothesis to somehow explain this incomprehensible number. At the same time, putting science first, Koonin reminds us that such a conclusion is too convenient, and that in order to stay within the framework of scientific discourse, we must lower the bar of assumptions and ruthlessly cut off the unnecessary stuff with a proverbial Occam's razor. Unfortunately, the dreamers won't like his conclusion. The emergence of life requires exceptionally unlikely events. Therefore, we are alone in our universe. Not only are we intelligent beings, but more broadly, the only living beings at all. Driven by cold calculations, this ruthless statement might not be the last piece of bad news for dreamers today. There is another barrier that seems just as insurmountable: the emergence of intelligence. It is a highly specific, complex, and insanely interesting topic. Although the rare Earth hypothesis has its fair amount of criticism, the counter-arguments mostly concern some very specific details. No matter how cruel the hypothesis may seem, it's still difficult to counter it with a more or less meaningful and well-argued alternative. But the facts are even more ruthless. Humanity has seen thousands of UFO cases, sent people to the moon and robots to Mars, has been listening to space with radio telescopes for many years, discovered thousands of exoplanets, and even launched spacecraft that left the solar system. And here we come back to our starting point. With our television and radio programs, we've been sending signals into space for about 100 years. We've also deliberately sent into space naive but daring signals for extraterrestrial civilizations. We've connected thousands of space enthusiasts on the internet to recognize signals received by the Arecibo Observatory in Puerto Rico as part of the legendary SETI program. Still nothing. Only silence. Even when the Arecibo radio telescope tragically collapsed, none of them seemed to be impressed. Nobody arrived. No one. But no matter how hopeless this great silence seems, it is by no means a verdict. Carl Sagan himself has been repeatedly saying his signature phrase, "Absence of evidence does not mean evidence of absence." At least because if the panspermia hypothesis is true, then life could well have gotten not only on our planet. This radically changes everything and turns the discourse on its head, and all these low probabilities don't seem significant after all. Finally, this never-ending search for extraterrestrial life, and moreover, intelligent civilizations, has one major flaw. We really have no idea what variables and what variable sequence make up the great formula of life. And we don't even know for sure what intelligence is and what forms it can take. Then why do we think that only terrestrial type intelligence is possible? Indeed, all this time we were looking for ourselves. But in fact, we are not even sure that life can only be carbon-based. Everyone who is at least a little interested in the topic has heard about the hypothetical silicone-based life forms. But that's not all. For example, when exposed to very high pressure, minus 460 GPa, nitrogen and hydrogen compounds become even more chemically diverse than hydrocarbons. It is therefore plausible that their derivatives are more diverse and numerous than all existing organic compounds. And here we are, only one step away from an alternative nitric hydrogen-based life. You can find suitable conditions for such biochemistry in the depths of the giant planets that contain huge amounts of nitrogen and hydrogen under extremely high pressure. But this is a completely different story and another set of probabilities. But we are still looking for ourselves and do it deliberately. This way, we have at least some idea of what to look for, because it's impossible to look specifically for something you don't have the slightest idea of. Stanislaw Lem spoke at length on this topic. Let us thus be honest with ourselves. We are not looking for any civilizations, but predominantly for anthropomorphic ones. We introduce the law and order of a scientific experiment into nature, and then, on the basis of such phenomena, we aim to see beings that are similar to us. Yet, we are not seeing any such phenomena. Is it because they are non-existent? There is something deeply saddening in the silence of the stars that awaits us in response to this question. A silence so absolute that it seems eternal. The great silence of the universe, supported by the rare Earth hypothesis, can really instill sadness or even fear. Fear of being fundamentally alone in the universe. But should we be afraid of loneliness or something else? There are so many things that can make you feel awe, and one of them is the grandeur of our universe. Have you ever wondered how vast and mysterious this boundless universe where we all live is? Imagine embarking on a journey aboard a spaceship, heading in one direction as far as possible from Earth. Now imagine that the spaceship can constantly accelerate up to the speed of light, and you have an infinite lifespan. How long would it take you to reach the edge of the universe? What would it look like? How would you cross it? And if you were to cross it, what would be beyond? Does the universe have an edge, or is it infinite? And what shape does our universe have? In this video, you'll find out the answers to these exciting questions about the boundaries and shape of our mysterious universe. What lies beyond the edge of the universe? Please leave a thumbs up. It shows YouTube's algorithms that this video is interesting and worth watching. It's 2023. An article published in Nature introduces a bewildering discovery by the new James Webb Space Observatory of 6 celestial objects that simply shouldn't exist. 13.8 billion years have passed since the Big Bang. Yet, these objects formed just 600 million years after it, in the nascent universe. We're talking about 6 galaxies, and notably, very massive ones. No one can wrap their head around the fact that such giants could have formed so early in the universe. Existing models suggest that these galaxies should be at least 10 times smaller, if not 50. According to calculations, there simply should not have been enough ordinary matter, the substance that comprises stars, planets, and ourselves, available at that time to form so many stars so quickly. If these findings are confirmed, we'll face an unsettling realization that we've been wrong all along. The widely accepted figure of the universe being 13.8 billion years old might be incorrect. In truth, the universe could almost be twice that age, an astonishing 26.7 billion years old. And this is not another amusing scientific oddity like, well, we didn't know this fact, but now we do, so good for us. This one genuinely has some profound implications. One of the study authors, Erica Nelson, said, "If even one of these galaxies is real, it will push against the limits of our understanding of cosmology. For now, there are no explanations for this anomaly, but wry suggestions for the concept of dark time that expedites the development of cosmic structures have already surfaced in discussions. Indeed, if all of this is confirmed, and it's not about the perfection of our observation methods, and no mistakes have been made, it will signify a crisis for our theoretical understanding of space. Despite our incomplete understanding of the universe's dimensions, we can assume that it does have some, however vague they might be. And if the universe has boundaries, then we could theoretically reach them, right? So what would they look like? Let's do a thought experiment to figure this out. Suppose we venture towards any point in the celestial sphere. Will this movement ever have an endpoint? And if so, what would it look like? Would we run into a black wall? Or perhaps pass through it? And if we did, where would we end up? For those who deem such speculations naive or even childish, it's worth noting that this question has perplexed humanity for millennia. A significant part of our past cosmology focused on the center and the edge of the universe. For instance, a 19th century engraving represents how medieval people imagined the boundary of the universe, beyond which lies the mechanism governing the cosmos. Admittedly, we haven't yet arrived at a definitive answer to this question. Today, we'll explore several of the most plausible theories. Please stay tuned for the end of the video, where we'll talk about the closest, most obvious, yet most elusive boundary. First, let's revisit some crucial points. If we were to take a powerful telescope and try to explore deep space, we wouldn't see the edge of the universe, but rather its hypothetical beginning. It's widely understood that when observing a person at the next table, we see them as they were 3 nanoseconds ago. But looking at the star Betelgeuse, we see it as it was 500,000 years ago. But it could have already exploded by now. Gravity works similarly. We perceive the sun as it was 8 minutes and 20 seconds ago. And our planet is gravitationally drawn not to the current location of the sun, but to where it was the very same 8 minutes and 20 seconds ago. And if the sun suddenly vanished without a trace, the Earth and other planets would continue orbiting an empty space before eventually scattering in different directions. For the same reason, Andromeda Galaxy, the largest galaxy in our local cluster, which is heading straight towards us at approximately 400,000 kilometers per hour, is really about 900 light-years closer than it appears. 900 light-years is a lot. To put this into perspective, the closest star to the sun lies 4.24 light-years away from it. But even with modern technology, it would take tens of thousands of years to reach it. In general, you get the idea, right? You can't just look at something and see it in real time. The farthest we can observe is the point from which light has had time to reach us since the Big Bang. The closest such point is over 46 billion light-years away. So immediately there comes a question of how this can be, considering the universe is only 13.8 billion years old. Are objects beyond this distance relics predating the birth of the universe? No, of course not. It's all about dark energy, and the rapid expansion of the universe it provokes. It's not that the light from the most distant objects has reached us, but rather space itself has expanded so much that we can see much further than the universe's age. Specifically, those same 46 billion light years in one direction. This is the boundary of the observable universe. While intriguing, it's not our primary focus, because it's almost certain that space extends beyond this boundary. However, we are seeking the real border, not just the visible one. First, let's try to tackle the problem head-on by asking the question, what would happen if we took a group of people, put them in a spaceship, and sent it in one direction in an attempt to reach the edge of the universe, considering that they would fly as fast as possible? David Kipping, an astronomer at Columbia University, has answered this question in the most detailed and intriguing way. Imagine that a spaceship can accelerate indefinitely at a rate of 10 meters per second squared. Why this particular rate? Besides the steady acceleration, this would make passengers feel as if they were experiencing normal Earth gravity. The ship's bottom would push the crew with the same effect as the Earth's gravitation. Now, let's keep in mind that the freefall acceleration on Earth is 9.8 meters per second squared, but we rounded up to 10 to make the calculations easier. Everything's clear, right? In the first second, the ship will travel at a speed of 10 meters per second. In the second, 20 meters per second. In the third, 30 meters per second, and so forth. After an hour, the speed will reach 35,280 meters per second and continue to increase by 10 meters per second squared. After 2.5 hours, the ship would whiz past the moon. After a week, past Saturn. 11 days in, it would fly past Neptune, the farthest planet in our solar system. For the sake of this thought experiment, let's dismiss practical concerns such as fuel supply and potential catastrophic collisions with cosmic dust. After 15 months of travel, the spaceship would have covered its first light year. At this point, its tremendous speed would already cause unusual phenomena due to the increasing influence of Einstein's special theory of relativity. At first, nothing prevents the spaceship from accelerating indefinitely. But a massive object like a ship cannot reach the speed of light. It can come as close as possible, but never reach it. For example, protons in the Large Hadron Collider are accelerated to a speed of 299,792,455 meters per second. It may seem like a mere additional 3 meters per second would be enough to reach the speed of light. 3 meters per second is an average jogging pace. But actually, no. Even if you spent all the energy in the universe to accelerate the proton by a measly 3 meters per second, it would only approach the speed of light incredibly closely, but wouldn't reach it. If not for this limitation, the spaceship would have surpassed the speed of light within 45 days. But something different happens in reality. The special theory of relativity postulates that the faster we move in space, the slower we progress in time. Therefore, some counterintuitive phenomena would happen in this situation. As the spaceship's speed approaches the limit, an outside observer would perceive the ship's speed as decreasing, with the onboard crew moving as if in slow motion. But from the perspective of the people on the ship, time would go as usual, and the acceleration would remain constant at 10 meters per second squared. Moreover, it would seem to the people on the ship that time outside the ship has sped up. Again, if not for the laws of the special theory of relativity, the ship would have exceeded the speed of light in 45 days. But in actuality, after 15 months of flight, it will only be moving at 87% of light speed. As the spaceship approaches the speed limit, time doesn't slow down evenly, but like this. That is, even when accelerating to half the speed of light, you almost wouldn't notice the time slowdown. When you reach 90% of the speed of light, time only slows down about twice. The extreme slowdown only begins when you closely approach the speed of light. For example, on October 15, 1991, a space particle named Oh My God reached us. It remains unclear what this particle was, but it got its name because its energy was equivalent to the energy of a baseball moving at a speed of 93.6 kilometers per hour. Just think about it. That's the energy of a single particle. This particle moved at a speed that was this percent of the speed of light. 99.999 several times over 51%. Scientists are yet to comprehend what propelled this particle and made it move at such a mind-boggling speed. Recent studies using the telescope array project have suggested that the source is in a 20-degree zone in the direction of the Ursa Major constellation. That's all we know so far. But it's scary even to imagine what it might be. The most amazing thing was that for this particle, the time slowed down. Just think about it, by a factor of 300 billion compared to a stationary observer. This means that while it would have taken 2.5 million years for us, the stationary observers, to travel from the Andromeda galaxy, the particle would have perceived it as less than 5 minutes. This means that time completely stops for light itself. The principle is clear, right? But the dramatic divergence in the time rates of our spaceship crew and the rest of the universe is only part of the problem. If the ship doesn't return, but just keeps flying, then after passing the 8.3 billion light-year threshold, there would be no coming back. Now this is truly amazing. Why? After all, there isn't any physical boundary there. But as soon as you pass the 8.3 billion light-year mark, that's it. You're trapped. Due to the expansion of space, the casual link with the solar system would be broken, and no amount of acceleration would ever allow you to return to its vicinity. This is all because the area of space where you are is moving away from Earth faster than the speed of light. It's not that you are moving faster than the speed of light, but that section of space itself. There are no violations of the laws of physics here because we are talking about space itself, not objects within it. An easy way to understand this is by picturing a slinky toy. If you stretch the slinky, you'll notice that each of its coils only moves a finger's width away from its neighbor, which is quite slow. However, during the same period, 2 coils at opposite ends of the slinky move over a meter away from each other. The same principle applies to galaxies in the universe. Due to this mechanism, distant galaxies can move away from us at the speed of light, or even faster. The same would happen to you if you fly far enough away from Earth. You would go beyond the edge to an area that's moving away faster than the speed of light. If you then decided to return to Earth, turn your spaceship around, and fire up all the engines, you'd still be moving away faster than you're approaching. It's terrifying even to think about the hopelessness that awaits the spaceship's crew. But that's only part of the story. An even more daunting reality awaits the crew. We need to take a step back to understand this. Remember, we said that due to dark energy and the expansion of the universe, our visual reach isn't limited to 13.8 billion light-years, but extends a full 46 billion light-years in one direction. And that's just for now. As space continues to expand in the future, this visible sphere will also expand, but only to a certain limit. Based on calculations, scientists estimate that our future vision limit will expand about 33% beyond the current limit, specifically reaching about 61 billion light-years away. This is the maximum limit to which, and we can't stress this enough, our visible universe can expand. However, being visible doesn't mean it's reachable. Dark energy, this powerful and yet incomprehensible force, has literally divided the universe into concentric regions. At a distance of less than 15 billion light-years, there are 66 billion galaxies. Theoretically, the galaxies within these limits are reachable to us. The crew of our hypothetical spaceship could reach them if it were moving at the speed of light. And someday in the future, Earthlings will be able to see these galaxies as they are right now at this very moment. The area that lies from 15 to 46 billion light-years away contains about 2 trillion galaxies. At such a distance, we'll always be able to see them, but for us, their age will never reach 13.8 billion years, and we'll never see these galaxies as they are today. They are beyond our reach, even if we could travel at the speed of light. If we were to observe them for tens of billions of years, we wouldn't see any development. For us, they will always remain as frozen, motionless farewell photos, slowly fading away until vanishing completely. Galaxies at distances from 46 to 61 billion light-years are currently invisible to us, but future generations will see them when their light from the past finally reaches us. However, these galaxies are already unreachable, even on a spacecraft traveling at nearly the speed of light. Galaxies lying beyond 61 billion light-years away cannot be seen or reached by us or anyone else, even in the most distant future. We've never seen them and have no idea what is happening there. Please keep in mind that we are not talking about some distant future, but what is really happening right now. For instance, consider the galaxy GN-Z11. This is one of the most distant galaxies we know today. Its age is 13.4 billion years, meaning its light was emitted 400 million years after the Big Bang. It's located at a distance of 32 billion light-years from us. We can still see it, but what we see is a farewell photo. The image of the galaxy GN-Z11 will slowly fade until it eventually vanishes forever. Because, as you understand, the light this galaxy is emitting right now will never reach us, unless, of course, the expansion slows down again. Right now, the galaxy GN-Z11 is moving away from us at a speed of 687,000 kilometers per second, over twice the speed of light. Unfortunately, this is exactly where the sad conclusions begin. The fact is that it goes far beyond GN-Z11. Think about it. More than 96.7% of the galaxies we can observe today have already vanished. The light they emit right now will never reach us. 98.6% of the galaxies we will ever observe have already disappeared. In other words, we are theoretically set to see a total of 4,700,000,000,000 galaxies. However, 4,634,000,000,000 of these are already beyond what we can reach, even if we could travel to them at the speed of light. And only about 66 billion galaxies still remain within our reach today. And please note that this is only a current estimate. This problem will only get worse over time. Right now, if we assume that each of the 66 billion galaxies has as many stars as the Milky Way, which is about 400 billion, it means that roughly 60,000 stars are disappearing from our field of view every single second. Tens of millions of stars have already disappeared since the beginning of this video. We'll continue to see their past light for billions of years, but any new light they generate from this very moment will never reach us again. Of course, they don't disappear in the full sense of the word. They continue to exist, just somewhere beyond our reach. But what difference does it make to us? We are no longer casually connected to these objects. Regardless of what we do from this moment on, we can't influence them anymore, nor can they influence us. Any information about these places is now fundamentally unattainable to us. For us, they simply cease to exist. If the force of space expansion can never overcome the gravitational force within galaxies, then gradually each of them will slowly sink into a complete darkness and solitude. Over time, existing stars will burn out, particles will decay, black holes will evaporate due to Hawking radiation, and the universe will be just empty space with only dark energy, ensuring its exponential expansion for eternity. Keep in mind that dark energy is kind of the opposite of gravity. That is, the more matter the space has, the stronger the gravitational force. Conversely, the emptier the space, the stronger the dark energy. As counterintuitive and odd as it may seem, its density per cubic meter doesn't decrease with the expansion of space. So do you see what is happening here? As the expansion of the universe accelerates, there will be more and more empty space, which will, in turn, accelerate the expansion process, resulting in even more empty space, and so on for infinity. Events in one part of the universe won't be able to affect what's happening in others. After all, going back to our previous point, the universe will be nothing more than an empty space, filled only with dark energy, making it expand exponentially. And now is a good time to go back to our imaginary spaceship. So what would happen if the crew kept flying at nearly the speed of light? By the time the onboard clock would strike the 200th year of the journey, 10 to the power of 41 years would have passed in the rest of the universe. That's 1 with 41 zeros. Due to the expansion of space, at this stage, it's statistically likely that there are no other particles within the observable universe aside from the ship itself. The spaceship would be traveling through a pitch-dark universe. Well, we can consider the first thought experiment to reach the boundaries of the universe unsuccessful. The universe would end faster than we could reach any hypothetical edge. But this is just the beginning. We're making these assumptions based on the premise that the universe is flat. Wait a minute. What? It's enough that we are puzzled by the theories of a flat Earth, and now a flat universe too? Luckily, it's a whole different story. To understand this, we need to delve deeper into the question, where is the edge of the universe? And does it exist at all? First of all, what makes us think that the universe, whatever it is, has any sort of boundary at all? Could it really be infinite? The javelin argument is an ancient logical argument put forward by the Greek philosopher Archytas to prove that the universe is supposed to be infinite. It goes as follows. What happens to a javelin when it is thrown over the outer edge of the universe? Will the javelin rebound? Or will it pass through and out of this world? If it passes through, then is there something else beyond the edge? If it rebounds, then the javelin is constrained by a certain barrier. But that barrier must also be constrained by something. And the thing that constrains the barrier must also be constrained by something, and so on to infinity. Hence, the universe is infinite. For more than 2,000 years, the most talented minds worked on this riddle, and it is safe to say that the riddle of Archytas has largely influenced the history of cosmology. However, what the ancients didn't realize was the possibility that the universe could be infinite and yet have edges. How could it be? We need to look a bit from afar off here. Everyone knows that the sum of the angles of any triangle is 180 degrees, but that's not really true. Back in the 19th century, one of the greatest mathematicians in history, Carl Friedrich Gauss, began to suspect something. Imagine if we, the inhabitants of a spherical planet, were not three-dimensional, but two-dimensional beings. Then our planet would basically become our universe. And in that case, drawing a small triangle on the ground and measuring the sum of its angles with ordinary instruments, we would get the exact same 180 degrees. But if we drew a triangle of enormous size, then Then, even with rough instruments, we would find that the sum of the angles was not 180 degrees, but greater. So Gauss hypothesized that our three-dimensional space might have curvature. If so, the sum of the angles of a large enough triangle should be noticeably different from 180 degrees. As far as we know, Gauss measured the triangle formed by 3 mountain peaks in Germany secretly using geodesic measuring devices, and found that the sum of its angles differs from 180 degrees, but differs within the permissible error, so the results cannot be taken into account. He did it secretly for an understandable reason. His colleagues, if they found out that a person is trying in earnest to find the error in the sum of the triangle angles, would have considered that Gauss went crazy. Many years later, Einstein's general theory of relativity was eventually verified by experiments far more accurate than those of Gauss. It turned out that in near-Earth space, the angles of the conventional Great Triangle can total 180.2 degrees. Today, this deviation from Euclidean geometry has to be taken into account, for example, in GPS satellite systems. Hence the question, if such curvature can be detected on the scale of the entire universe, it can give us an idea of its shape. The real shape, not what it seems to us from the inside. And it is curvature that can give us an indication of the universe's closedness. It can be hard to understand how the universe can be closed, with infinity in all directions, but everything becomes clearer if we take the closest analogy to the Earth's surface again. If we start moving in any direction, sooner or later, we will return to the same place. You see what happens? The surface of the Earth has no edge, and yet we realize that it's not infinite. So the universe may be similar, although on a three-dimensional scale. Imagine that the entire space of the universe is twisted into a kind of closed surface like this. You can't imagine it? Don't worry. Practically nobody can imagine it. So we settle for mathematics and vague ideas. And even at this stage of mental experiment, we can come to very unexpected and surprising conclusions, because the closedness of the surface can be different. And now get ready for the unbelievable. Scientists have already done a lot of work on this issue. They have theoretically discovered as many as 18 possible forms, i.e. topologies of the universe, and they are orientable and non-orientable among them. Let us explain what the concept of orientability is. For this purpose, we will consider an interesting two-dimensional surface, a Mobius strip. It can be created from a rectangular strip of paper, twisted once and glued at the ends. Now, take point A on the Mobius strip. Draw a normal perpendicular to it, and then draw a small circle around the normal in a counterclockwise direction when looking from the end of the normal. Let's start moving the point together with the normal and the directional circle along the Mobius strip. When the point goes around the entire strip and returns to the initial position, the direction of the normal will be reversed, and the direction of the circle will be opposite. Yes, visually it will be on the other side of the strip, but the surface has no thickness in geometry. Such trajectories are called orientation reversing paths, and surfaces that have them are called non-orientable or one-sided. Surfaces that do not have orientation reversing closed paths, such as a sphere, a torus, and a non-twisted strip, are called orientable or two-sided. So if we assume that our universe is non-orientable, then physically this would mean the following. If we fly from Earth along the orientation reversing closed loop, then we'll certainly return home. But we will find ourselves in a mirror copy of the Earth. We would not notice any changes in ourselves, but in relation to us, the rest of the Earth's inhabitants would have their hearts on the right. All clocks would work counterclockwise, and texts would appear in mirror images. It is unlikely that we live in such a world. Cosmologists believe that if our universe were non-orientable, energy would be radiated from the boundary zones where matter and antimatter interact. However, nothing like this has ever been observed, although it is theoretically conceivable that such zones may exist outside the observable area of the universe. Let's move on. What about the curvature of the universe? Scientists did manage to measure the curvature of space at great distances and found no distortion. That is, the universe is really curved locally near massive objects. But if measured as a whole on large scales, it's flat within the error of measurement, and that points in favor of its infinity. And that leads to some pretty staggering conclusions, one more unbelievable than the other. The theoretical physicist Max Tegmark writes in Our Mathematical Universe that the number of all possible combinations of particles in the observable universe is about 10 to 10 to the 118th power. This is an unimaginably huge number. But if the universe is infinite, that means if you draw a straight line from the Earth in any direction, then after 10 to the 10th to the 118th power of the diameter of the observable universe, that line would meet the exact same Earth with the exact same observable universe where your copy is doing and thinking the exact same thing you are doing at this moment. Well, it's already a bit better than a reversed universe, as in the case of the Mobius universe. But is it really better? It all seems kind of crazy, but there is not a single law of physics that would prohibit such a state of things. In fact, if the universe is truly infinite, it leads to horrific philosophical consequences. Believe me, you wouldn't want to live in an infinite universe. Now, this mental experiment of Max Tegmark is just a walk in the park compared to the absolutely incredible conclusions that follow directly from the assumption that the universe is infinite. The point is that even a completely empty infinite universe only appears to be empty. Ask yourself two questions. The first one, what would happen if you had an infinite amount of time? And the second one, what would happen if you had an infinite amount of space? The answer to both of these questions is everything. Literally everything within the laws of physics. We understand that it sounds implausible, to put it mildly, and not very clear. You'll get it in a moment. An empty universe is never completely empty, because even where there are no particles, there are still quantum fields that are never completely quiet. Quantum fields do not maintain a constant value, and their value at any location in space is always a little bit shaking, trembling. In scientific terms, this shaking is called quantum fluctuations, and they are nothing but consequences of the famous uncertainty principle of Heisenberg. This is not some fantasy. This is modern quantum physics, the most effective model proved experimentally with inconceivable accuracy. And at the quantum level, if we had the ability to wait long enough, from time to time, we would witness really strange things caused by unpredictable fluctuations. In an ever-expanding universe, time and space become so vast that extremely unlikely events can and will happen with 100% probability. You may ask, oh, come on. Are you saying that if you wait even an unimaginably long time, then a piano, for example, can spontaneously appear in a completely empty universe out of nowhere, out of these quantum fluctuations? What nonsense. You may be surprised, but this question was seriously addressed by the most prominent physicist of our time, Anthony Aguirre, Sean M. Carroll, and Matthew C. Johnson. And they even calculated the probability of such an event. If you wait for a period of time 1 trillion years longer than the age of the universe, you will see this piano appear right before your eyes. Once again, as crazy as this may seem, it is all a direct consequence of the laws of physics at the level scientists understand them today. The less likely an event is to happen, the longer you have to wait. But if you have infinite space or infinite time, and especially if you have both, then any unlikely event will happen an infinite number of times. That's the horror of infinity. In infinite time, it is our universe that will repeat itself sooner or later, with any accuracy. And you will watch this video again, and it will be repeated an infinite number of times. A lot of people won't be happy about that, and a lot of people would prefer the universe to be closed without all those horrible infinities. But there are two things here. First, the universe may still be closed, but simply warped on extremely large scales. And we, like Gauss, may not have the right measuring instruments. So our measurements say that the universe is flat with 99.75% accuracy. That means that if the universe is not flat, it must be at least 400 times the size of the observable universe, 37,200,000,000,000 light-years in diameter. And secondly, the universe does not have to be curved in order to be closed. Take, for example, the surface of a cylinder. It is geometrically flat because parallel lines drawn on the surface remain parallel. This is one of the definitions of flatness. And yet, it can have infinite dimensions. The same could be true for the universe. It could be perfectly flat, but at the same time, still closed. For example, while in a universe that is a four-dimensional sphere, the sum of the triangle angles would be greater than 180 degrees, and parallel lines would intersect. Nothing of this would be true in a universe in the form of a four-dimensional torus. The space will appear flat there. However, moving along a straight line, sooner or later, you will return to the place you came from. In the end, it all comes down to the shape of our universe, a shape that could only be seen by a four-dimensional being. And here we come to a conclusion that will be surprising to many. In conclusion, we will finally explain what was meant at the very beginning of the video about the edge of the universe always in front of our eyes. Let's say more. This edge is not only in front of our eyes, but it is everywhere. We're talking about the fourth spatial dimension. Here's what it looks like. Imagine a conventional two-dimensional world. It can be infinite in all directions, or spherical, or closed toroidal, whatever you prefer. And imagine it contains some two-dimensional matter of its own. There might even be strange two-dimensional beings living there. If we imagine that they have a semblance of our eyesight, the world would look pretty bleak to them. Now let's imagine that this two-dimensional universe is in our three-dimensional universe. What we get is that the whole underside of this world is revealed to us in great detail. Imagine that a two-dimensional world also consists of two-dimensional molecules and atoms. So we, three-dimensional beings, can see every atom of this two-dimensional world as if it was spread before our eyes. And it is crystal clear where the edge of this two-dimensional universe is. Here it is, isn't it? If we make a direct analogy with our three-dimensional world and wonder where the fourth dimension is, the answer is surprising. It is everywhere. Absolutely everywhere. Around every atom. Around every tiny fragment of space. We are literally saturated with this fourth dimension, although we almost cannot interact with it in any way. And it's also true, the edge of our universe. So far, the only one we can be confident about. But there is something that remains ever elusive, shrouded by a veil of mystery and enigma, where emptiness begets emptiness. Imagine a place where there is nothing for millions of light years ahead. Absolutely nothing. Total darkness. A place so dark that it seems that time itself is put on hold. But what is it? Let me explain. We know that we orbit the Sun, and the Sun orbits the center of the Milky Way galaxy. The Milky Way, along with its 50 neighbors, goes around the invisible gravitational center in the local galaxy group located inside the Virgo supercluster. Just like other superclusters, it turned out to be a part of a much bigger Laniakea supercluster. Inside the circle, the objects don't orbit the same point, but gravitate towards a super-heavy great attractor anomaly in the center. We can't see it due to the specific location of our galaxy. Our galactic disk obstructs our view. But today, we're interested not in the attractor itself, but the eerie, empty space in front of it. Dipole repeller. Such empty areas in outer space are called voids. And if you look at the universe from the outside, it would seem like an infinite network of galactic threads divided by empty spaces called voids. This is what our world looks like if you could capture it in one picture. 10 billion light years connected with galactic threads. Voids are one of the biggest structures in nature that occupy most space in the universe. Today, we will focus on one of these voids. This is the Boötes Void. When we gaze at the stars, it seems that they are dispersed evenly throughout the sky. But this is an illusion, as all stars are in galaxies. They are located relatively close to each other, making gravitational clusters. But the emptiness created between them is nothing compared to the scale of the void. The Boötes Void is one of the biggest voids in the whole universe. It is located 700 million light-years away from our planet, near the Boötes constellation from which it borrowed its name. The Great Void was discovered in 1981 by Robert Kirshner and his team. For many years, scientists have been asking themselves about the nature of this void, how it was created, and what exactly lurks in the darkness. The diameter of the Boötes Void is estimated to be 330 million light-years, which is astonishing considering the fact that it comprises 0.27% of the diameter of the known universe. The size of our Milky Way galaxy is about 100,000 light-years, which is minuscule compared to this void. When scientists first started to study the void, they discovered 8 galaxies. This is very little compared to other gravitational clusters which have already been explored. Before long, 52 more galaxies have been discovered at a great distance from each other. According to astronomer Greg Aldering from the University of Minnesota, the scale of the void is such that if the Milky Way had been in the center of the Boötes Void, we wouldn't have known there were other galaxies until the 1960s. They would have been so far away that they would have been invisible to the telescopes that existed up until the 60s. At that point, our telescopes got good enough that if we had been in that void, we would have been able to see the dim light from the other galaxies and begin to fathom their existence. So far, only 60 galaxies have been found in the Boötes Void. Using a rough estimate of about one galaxy every 10 million light-years, 4 times as far as Andromeda Galaxy from Earth, there should have been approximately 2,000 galaxies in the Boötes Void. Upon discovering this great void, astronomers have noticed how mysterious and unique this area is. When taking into account the distance between the galaxies inside the void, it's clear that it can be called a paranormal area. Just to put this in perspective, our Milky Way galaxy has around 24 neighbors in the space of around 3 million light-years in the cross-section. Taking into account that the average distance between galaxies in the universe is around several million light-years, the Great Boötes Void should have included 10,000 galaxies if dispersed with the same density. You can agree that the difference in density is just enormous and can't be explained rationally. Scientists have managed to calculate the volume of the Great Void. They assigned it a non-system value called parsec, which equals 3 light-years. Now, you'd be surprised to know that the estimated volume of the Boötes Void is 236,000 cubic megaparsecs. Let's leave aside the size of this void and focus instead on its content. It sounds paradoxical, but the void mostly consists of emptiness. Its vacuum space is isolated from everything that you can observe in other galaxies. You won't see any dust, dirt, or stones there. There's no place for even the smallest particles, such as photons. This is why scientists call the Boötes void a desert in outer space. The Boötes void is submerged into darkness. It is so dark that it seems that time itself or any movement is put on hold. To this day, scientists don't understand how simple particles interact in this space. Unfortunately, we might not know this for many years to come. Even if the interaction can happen, how many tens of thousands of years are needed for this process to take place within the void? Compared to this time frame, the history of mankind is like a blazing meteorite flying through the Earth's atmosphere. The nature of the Boötes void gives us a lot to think about. Needless to say, the void's visitors would be at the very least shocked to see this isolation, extreme distances between galaxies, and pitch-dark space. Moreover, the Boötes void is probably the most ideal vacuum in outer space, so we should study its effects. Dirt and dust would be rare to come by in this space, but so would even particles. It would take thousands of years for the particles to interact. That is, if the interaction could ever happen in the first place. This extremely low density means that when a pattern of neutrinos enters one side of the void, it looks exactly the same upon exit. The same goes for photons. Particles of matter, having much more mass than both photons and neutrinos, would of course get pulled towards the walls of the void. Because of this state-preserving property, the Boötes void may one day be seen as the ultimate time capsule. Fire off a pattern of photons, only for the pattern to be rediscovered hundreds of millions of years later when it reaches the other side. Perhaps the Boötes void will serve as a proving ground for the high-speed dragsters of the future, moving at 99.99% the speed of light. Its extremely low density would certainly be appealing to anyone who wants to set speed records without that pesky intergalactic dust getting in the way. Of course, scientists are keen to know how this paranormal area came to be. The Boötes void is a unique place that cannot be compared to anything within the known universe. Some scientists argue that the Great Void was created when several small voids came together. Even though this idea is hard to comprehend, it's completely plausible, taking into account the nature of space. This phenomenon resembles small soap bubbles coming together. Astronomer Greg Aldering once noticed that the galaxies located in voids have a curiously tubular structure, which can be an important clue. It was him who suggested that the void can come together much like soap bubbles merging into one great bubble. As for the tubular galaxies, these might be the remnants of the borders between the smaller voids. Those galaxies are stranded now inside a supervoid. But if the universe lasts long enough, they may get cleared out of it. Says Aldering, the long arm of gravity never quits. There is another, albeit more radical possibility, and one that has likely not been considered in the scientific literature. The Boötes void could be the result of an expanding Kardashev 3 scale civilization. As the colonization bubble expands outward from its home system, the civilization dims each star and subsequently each galaxy it encounters by blanketing it in a Dyson shell. This might also explain why the void has such a nice spherical shape. Given that the void is about 700 million light-years from Earth, and that intelligent life could have emerged in the universe about 4 billion years ago, this ancient civilization may have had enough time to perform this astonishing feat of cosmological engineering. Now, this is pure speculation, but it's worth throwing it out there as a possibility, given the strangeness of this phenomenon. Needless to say, the discovery of the void has thrown conventional cosmological thinking out the window. Since its discovery, astronomers have had to revise their notions of galaxy formation, given what we now know about the extreme non-uniform distribution of matter throughout the universe. Finally, the Boötes void provides another humbling reminder of the vastness and sparseness of the cosmos. The universe that we see is too impossibly large for us to comprehend. Our place within it is a tiny, insignificant microscopic spark. But all that said, and as alone as we may appear here on Earth, at least we have a starscape to gaze upon when we look up into the night sky. Gazing at the night sky, we contemplate the myriad scenarios and alternate versions of our own lives in an infinite multi-dimensional reality. Have you ever thought about the existence of parallel worlds, where your life could be completely different? Do you think this could be real? Maybe your life's integrity is an illusion. We all perceive our life as one continuous journey through space and time. In reality, we are an exponentially growing set of events that branch out from moment to moment. There can be multiple versions of you. So, in a way, you can call yourself immortal, as somewhere always exists another version of you. In this video, we'll present a lot of interesting facts. You'll find out what cosmic microwave background radiation is, why it's so interesting, what evidence supporting the existence of the multiverse has been found, whether you have a chance for another life, and finally, what Schrödinger's cat and Einstein have to do with anything. Furthermore, we'll dispel several entertaining myths along the way. The first ever evidence of the multiverse. Please subscribe to our channel and hit the like button. This story began in 1948, when a Russian-born American physicist, Georgy Gamow, calculated that radiation with a temperature of about 50 degrees Kelvin, or minus 267 degrees Celsius, should have formed during the Big Bang that gave rise to the universe. Later on, it turned out that the scientist was mistaken by more than an order of magnitude. The radiation temperature was only 2.7 Kelvin. This radiation was accidentally discovered in 1965 by radio astronomers Arno Penzias and Robert Wilson at Bell Laboratories. They used a radio antenna built in the early 1960s to work with one of the first echo communication satellite systems. The satellites were outdated. They safely burned down in the oceans, and scientists got a hold of the antenna. Penzias and Wilson actually wanted to register the emission of neutral hydrogen, which is abundant in the universe, but the microwave noise constantly interfered with their measurements. Oddly, they couldn't identify the source, as it seemed to be coming from all directions. They tried to explain it by New York, the military and their tests, and virtually by everything that came to mind, even the pigeon droppings that interfered with the antenna. The litter was cleaned, but the noise remained. Only later did they understand the nature of this noise. It was microwave background radiation that scientists were looking for so long, only to be discovered by accident. For this very accident, these two scientists received the Nobel Prize in 1978. It became clear right away that having made a mistake in the temperature value, Gamow was right about something else. The cosmic microwave background radiation was indeed ubiquitous and isotropic. That is, it came from any point in the universe and had the same temperature everywhere. Our world is literally immersed in this radiation. Of course, there were some minor root mean square deviations of the cosmic microwave background temperature, as the theory predicted. On average, their value is 18 microkelvin. That is a number with a bunch of zeros, minus 0.000018. So if you color code the temperature of the cosmic microwave background radiation on the map of the starry sky, the coldest areas marked with blue and the hottest areas marked with red, it will look like a patchwork quilt or light ripples on the surface of the water. And now let's talk about the great mystery of the universe. In 2004, the American WMAP satellite was performing some routine research for mapping universal microwave radiation that emerged 380,000 years after the Big Bang. When the data was pieced together and processed, it revealed something unusual. And this is what it looks like. The circled area is a cosmic microwave background cold spot. That is, this area is even colder than the universal microwave background radiation. One might wonder, what's so special about it? In fact, there are two things. First, this area is significantly colder. As we said, an average temperature deviation is 18 microkelvin, and here it is 70 microkelvin, and can go as high as 150 microkelvin in the center. If the cosmic microwave background radiation is represented by the sea, and its temperature fluctuations appear as waves, then the average fluctuation of 18 microkelvin would be a slight ripple. And now imagine that among these ripples, you came across a section with several meter-high waves. And this area is just huge. But there is actually one more thing to make your jaw drop. The cold spot is almost 2 billion. No, not kilometers, but light years long. To put this in perspective, our Milky Way galaxy is only 100,000 light years across. So this universal refrigerator can store as many as 20,000 of our galaxies. And another bit of information, the US has the area equivalent to about 8,000 New York cities. Don't you just love these scales? But what is this area right here? Where did it come from? According to standard cosmological theory, low temperature accompanies low density. That's easy to understand. Take, for example, some hot gas. If you allow it to expand, then its temperature and density will start to drop. So scientists have discovered a truly humongous void, the supervoid. Since it was found in the Eridanus constellation, it was dubbed the Eridanus supervoid. If somebody got to its center, they would be submerged in total darkness. It's impossible to navigate there. No gravity, no stars, freezing cold, an ominous place. Probably this is the darkest place humanity has ever known. But how did it come about? Scientists have known about voids for quite a while. These are vast areas between galactic filaments where there are hardly any galaxies or clusters. Therefore, their density is about 10 times lower than in other parts of the universe. Voids were first discovered in 1978 by Stephen Gregory and Laird A. Thompson at Kitt Peak National Observatory in Arizona. They range in size from 30 to 300 light years. But 2 billion years is too much. Moreover, some computer simulations performed within the framework of the generally accepted Big Bang theory have confirmed that voids should arise, provided that the universe expands evenly. But it can't explain the Eridanus supervoid. With such a size, such a low density, and such a low temperature, it simply can't exist. Scientists have put forward several explanations as to how this giant anomaly appeared. For example, that it's a huge black hole that absorbs everything coming its way. It will expand and eventually swallow the Earth along with people. But don't you worry. First, the Eridanus constellation is 3 billion light years away, so it will take a very long time indeed. Secondly, calculations show that such a black hole can't exist. After all, don't forget that for all its hugeness, this area is actually empty. For example, a black hole weighing 100 million solar masses is actually smaller than the Sun itself. The second hypothesis is as follows. According to the standard cosmological theory, Our universe is filled not only with regular or so-called baryonic matter, but also with dark matter. It doesn't take part in electromagnetic interaction and therefore cannot be observed. But it's involved in the gravitational interaction. According to some American researchers, there shouldn't be any dark matter in the Eridanus supervoid. Otherwise, it would be much heavier and would be evidenced by higher radiation temperature. Isn't this ironic? A huge dark void has no dark matter. So maybe there is no dark matter after all. And if there isn't, then the Big Bang Theory is also wrong, and therefore it doesn't make sense to explain Eridanus supervoid with it. But this might have gone too far. There are a lot of objective observations proving the existence of dark matter. So what is this cosmic microwave background cold spot anyway? Is there a more plausible explanation for this huge phenomenon in every sense of the word? There is. Moreover, not only is this explanation plausible, it's super exotic. This cold spot may be the first real proof of the multiverse, the infinite number of worlds, and possibly some alien civilizations that exist outside the known universe. Perhaps this spot was left as a result of our universe colliding with another universe. Just imagine, we can see the aftermath of the collision of entire universes. This is too much to take. But how is this even possible? Let me explain. In 2017, a PhD student, Rory Mackenzie, and Professor Tom Shanks of the Center for Extragalactic Astronomy at the University of Durham, England, proposed a rather unusual explanation. At first, Professor Tom Shanks frankly stated that the standard cosmological theory allows for such a wide-range temperature fluctuation. The scientist estimated the likelihood of such an event as 1 in 50. But this is too small a chance to trust reliability of theory. Therefore, Shanks and Mackenzie have put forward another explanation that unequivocally explains the existence of this cold spot. They argue that this is not even a void, but a place where our universe collided with another bubble universe. This statement is supported by other physicists, namely Anthony Aguirre, Matt Johnson, and Matt Kleben. Their works proved that a collision between our bubble universe and another bubble in the multiverse would leave an imprint on the cosmic background radiation that would resemble a circular spot with either more or less intense radiation. This is actually what we observe. But then the big question arises: does the multiverse really exist? According to one of the interpretations of quantum mechanics, it does. Quantum mechanics studies the phenomena of particle interaction and determines its laws. Let's consider it in more detail. This story begins with Young's double-slit interference experiment. If we were to project small, firm balls at the plate with a slit, we would see a line on the screen at the site of impact. If we make another slit in the plate, we will naturally see 2 lines on the screen. Now let's see how the waves behave under such conditions. The waves pass through the slit and hit the screen with a greater force precisely along the slit. But something unexpected happens when we add another slit. We would see an interference pattern on the screen, like this one. That is, there are not 2 lines, but a lot of them. This is absolutely typical for waves and can be solely attributed to their properties. So far, everything is clear. But let's look at the same experiment done with an electron as a projectile. If we throw electrons through one slit, we will see one line on the screen, just as in the case of firm balls. But when passed through 2 slits, electrons won't form 2 lines on the screen as expected, but rather quite a lot of lines, as is the case with waves. Physicists have long wrapped their brains around this fact. They hypothesized that electrons may hit each other, which is why they are cast aside in different directions. This creates an interference pattern with many, many fringes on the screen. Then, physicists started to shoot electrons one by one, so as to eliminate the slightest chance of their collision. But here's the fun part. Yet again, scientists saw the same interference pattern on the screen. That is, quite a lot of lines. But how can elementary particles create a pattern the way waves do? After all, they were released one at a time. Nobody understood this. Then, physicists decided to see through which of the slits the electron was passing. They put a measuring device near one of the slits to register the passing of the electron at that particular site. Then, something even more exciting happened. The picture on the screen changed dramatically. Now, there were two lines instead of an interference pattern, just like in the beginning when scientists fired firm balls at the plate. That is, the very fact that scientists observed the electron affected the experiment's results. It turns out that observation really affects the course of events. As a result, two theories have emerged explaining particles' behavior. The first theory is the Copenhagen interpretation, an idea put forward by Heisenberg and Bohr. In a nutshell, the theory proposes that an unobserved particle flies through one of the two slits as a group of equally probable particles in different positions and interferes with itself. Einstein and Schrödinger didn't like this interpretation. It was Einstein's famous phrase, "God does not play dice," that referred to this idea. More precisely, Einstein said, "I am at all events convinced that he does not play dice." Although the phrase retained its original meaning, it was then distorted to "God does not play dice." Schrödinger proposed a famous thought experiment with a cat, which is actually an argument against this Copenhagen idea that is often confused with proof. In simple terms, there is an atom that can either disintegrate or not disintegrate. Until this has been verified, it's in a state of superposition, that is, in both states simultaneously. Let's try and take this superposition state to the macro level, that is, not the atom level, but to the level of large bodies. We can do this by linking the decay of the nucleus to a major change. For example, the cat's death. As such, an atom can be considered in superposition, while the cat cannot, because no one has ever seen a broken and whole cup at the same time. It's always either broken or whole. This means that the idea that a particle can be found in either of two states with an equal probability is nonsense. We need to find another explanation. By the way, the Schrödinger experiment considers not a male, but a female cat. Then another theory appeared, one that presupposes the existence of parallel worlds. Each version of life begins to exist in its own separate reality, which is in no way connected with others and has a life of its own. It's like Dr. Strange. It turns out that there exist all possible scenarios, but we randomly find ourselves in only one. The most surprising thing here is not the idea of alternative worlds, but the fact that it's proposed by scientists and not by sci-fi writers. It's called the many worlds interpretation of quantum mechanics. If it is correct, then there is an almost infinite or an infinite number of versions of you, each perceiving the world as an individual and having no idea about the existence of other counterparts. Consequently, the very number of alternative life trajectories is extremely high. From the time you were born, or what seems to be you has taken different paths in different worlds. The complete set of you is a massive root system that grows exponentially, with each root representing a new life. As always, the more answers you have, the more questions arise. Let's think about our multiverse, about the multitude of worlds and alternative lives, where every decision affects the outcome of events. And here's an interesting question. What if our entire multiverse is just a simulation? there are actually several compelling arguments supporting this theory. Do you have any idea how many times computer capabilities increased from the 1940s to the present day? Take a guess. Hundreds of times? Thousands? Well, actually, they've increased by hundreds of trillions of times. And this is just the beginning. Many scientists predict that computer capabilities will increase by millions of times in the coming decades. This means we'll be able to create virtual worlds so complex that their characters will be as complex as we are. In other words, they would have consciousness just like us, but they wouldn't know they are living in a simulation. Wait a minute. What if? What if we are those very characters? Sounds preposterous, doesn't it? But does it really? For instance, Elon Musk firmly believes that we are living in a simulation and often talks about it in interviews. He literally said, "There's a 1,000,000,000 to 1 chance we're living in base reality." But Musk is not alone here. More and more people with academic degrees are saying the same thing. Today, we'll find out the odds of us really living in a simulation, what evidence points to this, and explore the implications of this knowledge if in fact this is true. Do we live in a simulation? Please give us a thumbs up. Your like helps YouTube algorithms understand that this content is worth watching. To understand the first piece of evidence, we need to know the basic principles of how computer games, simulations, and metaverses work. We move our character within a game, and the game engine quickly generates the entire surrounding in front of us. City streets, cars, other people in the game. All of this appears only at the moment when the character is looking at it. There is simply nothing outside of this field of view. Absolutely nothing. Not even emptiness. Or let's say you're wearing VR glasses. When you look straight ahead, everything behind you doesn't load, and it doesn't become visible or real until you turn your head. Yet, whatever has been in front of you instantly vanishes as soon as you turn around. But then, when you take off the VR headset and look at the real world, everything unfolds exactly the same. So the question is, how do we know that something exists if we're not directly looking at it? What if the universe really uses the same principle, showing us whatever we observe? This is where we come to the evidence suggesting that our world is virtual. The first piece of evidence. You might be familiar with the observer effect. This fascinating phenomenon became recognized as a result of Young's experiment, also known as the double-slit experiment. YouTube is full of detailed explanations and demonstrations of this experiment, all because it is the most famous experiment in the history of physics, which has been repeated the most number of times, with the most shocking results and the most accurate measurements ever. In a nutshell, the experiment boils down to the following. Light behaves in a very strange way when its structure is scrutinized. As we know, light is electromagnetic waves. However, when you start measuring the properties of a specific light beam with the greatest precision, it no longer behaves as a wave, but as a stream of particles. There is no contradiction or error here, merely a paradox scientists encounter when delving into the subtle levels of matter. To put it simply, when unmeasured, light acts as a wave, but when measured, it acts as particles. This might sound unconvincing if you talk about such semi-abstract things, but in fact, this is quite a startling paradox. It's like saying that when you look at a cup of coffee, it's a cup of coffee, but when you don't, it's the sound of the sea. In other words, if you observe light with high precision, it abruptly changes its basic characteristics, as if it knows it's being observed. Once again, this explanation is very simplified and doesn't describe all the amazing effects discovered during the experiment. The Young experiment has been replicated by various scientists and enthusiasts an unimaginable number of times, each time confirming that everything indeed works in this unfathomable way. One might ask, what difference does it make what happens in this quantum world? However, similar effects were observed not only with light, but also with electrons and individual atoms, the basic building blocks of all matter that surrounds us. This train of thought takes us to a staggering conclusion. Does this mean that if I'm not observing the moon, it doesn't exist at that moment? Well, it turns out so. Although, of course, everything is much more complex than that. We simplify it just to make it easier for you to understand the next argument. The second piece of evidence. Now let's consider another peculiar setting of our world that blatantly stands out: the speed of light. It is constant, unchangeable, and cannot be exceeded under any circumstances. Doesn't it instill a sense of doom, or even a little unfair? You can't help but say, what the hell? But let's look at the speed of light from a different perspective. For instance, let's consider the clock speed of your laptop or smartphone processor. It's a fixed number of gigahertz, clearly stated in the technical specifications. You can't exceed it. It's simply impossible. Somehow, we calmly accept this as a given. How else could it be, after all? Yet, the limitation of the speed of light sparks outrage in many of us. So, what if the unalterable speed of light merely reflects the maximum computing power of the mysterious machinery controlled by even more mysterious architects of our world? A world that might actually be a simulation. The fixed limit of 300,000 kilometers per second does seem peculiar. Let's see how it works. As an object's speed increases, its time slows down. This has been proven by numerous experiments. We know this for certain. Time completely stops for any object moving at a speed of 300,000 kilometers per second. This means that if you had a spaceship capable of accelerating to the speed of light, and you decided to fly to a distant galaxy 3 billion light years away, you'd get there in an instant. But it would only be an instant for you, as the time on the ship would completely stop during the flight. However, back on Earth, 3 billion years would have passed. So photons of light indeed move at a speed of 300,000 kilometers per second, and therefore their time stands still. This makes it impossible to go any faster, because to increase the speed, you'd have to slow down time even more, which is already at zero. This raises a question. Why is it that speed slows down time in our universe? Why are space and time interconnected? Why on earth does our reality have such a strange limitation? Why should it be there at all? It seems highly unusual for a physical world, but perfectly reasonable for a virtual one. If we live in a computer simulation, then the speed of light might be a product of information processing. Information. Please bear this word in mind. The speed of light limitation is often described not only as something cannot move faster than light, but as information cannot be transmitted faster than the speed of light. Don't you see this striking analogy with the world of information technology? It seems that the principle of information exchange in our universe resembles that within our computers. The third piece of evidence: discreteness of space and time. In modern physics, there is a measurement system called the Planck unit. According to this system, the smallest measurable unit of space is 1.6 times 10 to the power of minus 35 meters. It's impossible to measure a length smaller than this unit. What's more, this is the minimum length that can possibly exist. There is simply nothing smaller than this in the universe. Even empty space is not continuous, but consists of such infinitesimally small chunks. Moreover, segments shorter than this cannot exist in our physical universe. Otherwise, all known physical laws would be violated. Doesn't this ring a bell? It's literally like pixels on a computer screen. The image on the screen can't be smaller than 1 pixel. But the story doesn't end here. This pixelated nature of the universe has further implications, and it's truly breathtaking to realize them. Bear with us for a bit. Pixels on the screen exist constantly, whether light is projected on them or not. Similarly, cells of space the size of 1 Planck length constantly exist in the physical universe, and they do so regardless of whether there's something in them at a specific moment. You probably know that the screen doesn't continuously emit light, but refreshes at a certain frequency. The most common is 60 Hz, 1/60th of a second. The image on the screen changes during this brief period. Similarly, in the physical universe, there's a minimum measurable time akin to the minimal length known as Planck time. This amount is also infinitesimally small, 5.4 times 10 to the power of minus 44 seconds. As light travels through space, it sequentially occupies adjacent cells of space, one after another. The movement of a quantum photon of light between neighboring cells occurs instantaneously in a leap, since a quantum is indivisible and cannot travel in parts. The time light spends in one cell equals 1 Planck unit of time. The cells of space are stationary, so while light occupies a cell, it remains stationary too. Taking into account the size of the cell and Planck time, you can calculate the maximum speed of light. This means that the speed of light is determined by the size of the cell and the minimum unit of time. As a photon jumps from one cell to another, staying in them for only 1 Planck unit of time, it reaches the maximum speed of 300,000 kilometers per second. Planck time suggests that the universe exists for this brief duration. Then it seems to completely vanish, only to rematerialize during the next Planck unit of time. The universe flickers, just like the image on a computer screen. The sole difference is that a computer screen refreshes 60 times per second, while the universe refreshes 5.4 times 10 to the power of minus 44 times per second. Our senses can't detect such a high refresh rate of the universe, and so we perceive the world as continuously existing, just like we don't notice the flicker on the computer screen. Finally, here is the currently strongest 4th piece of evidence that we live in a virtuality. This is quantum entanglement. To understand its essence, we need to look at it from afar again. Imagine a microparticle, such as a photon of light, flying through space. Each such particle has a characteristic: spin. Very roughly, it can be compared to the spin direction. In fact, the photon does not rotate at all, but for the sake of understanding, let's assume such an analogy. So when all physicists on the planet puzzled over the reasons of such mystical results of Jung's experiment, Einstein, who did not like this mysticism at all, proposed an interesting experiment which would have to disprove the observer effect. Its essence is as follows. If a cesium atom emits 2 photons in different directions, their states get interrelated because of the law of conservation of momentum. This is called quantum entanglement, and it's determined by spin. If one of the entangled photons spins from top to bottom, then the second photon should spin from bottom to top, i.e., have the opposite spin. It's unambiguous, and there are no exceptions. It's like a pair of gloves. If one of them is right, then the other is definitely left, sure as hell. And experiments confirmed it at first. Indirectly, it turned out that the entangled photons already contain information about what spin they possess. But Jung's experiment, which was repeated, checked and rechecked in Einstein's time for countless times, proved that the entangled photons just have no idea what spin they should have, until they're measured. It seemed that Einstein was right once again, and there was something wrong with quantum physics. But 17 years after Einstein's death, another scientist, John Bell, did something impossible. He came up with one incredibly cunning and very complicated experiment that would prove or disprove the theory that elementary particles have information about their spin embedded in them in advance. The experiment results were astonishing. They clearly and explicitly showed that before observation, particles really know nothing about how they will spin when their state is measured. Simply put, before the measurement, they just don't have any spin. This property only appears after the measurement. The photon randomly chooses its spin, and that's why the comparison to gloves is inappropriate. Okay, so what? It appears that entangled particles can easily transmit information to each other much faster than the speed of light. If you spread the entangled photons even to different ends of the universe, measure one of them, and find out that it has an upspin, then the second one will have a downspin instantly. Physicists were totally stunned by this. No one could understand how such a thing was even possible. In 2008, a group of Swiss researchers from the University of Geneva set out to determine how quickly the second entangled particle learns that the first has been measured. They scattered two entangled photons 18 kilometers apart, measured one particle, and began to record the rate at which the second particle would react to it. The scientists had the technology to detect a delay of 100,000 times the speed of light, but no delay was detected. That meant that entangled photons could communicate with each other at least 100,000 times faster than the speed of light, and most likely instantaneously. Although Einstein was wrong about entangled photons, he may still have been right about one thing. That's when he said that instantaneous communication in the physical world was impossible. Well, maybe it is impossible in the real physical world. What he didn't realize is that we are probably living in a digital virtual reality. And that's where instantaneous communication is very easy to explain from this point of view. Let's say photons are some sort of equivalent of pixels on a screen. When two pixel photons become entangled, their programs combine to jointly manage the 2 points. If one program is responsible for the top spin and the other for the bottom spin, their joining will be responsible for both pixels, wherever they are. When one entangled particle is measured, its program randomly selects one of its spins, and the program of the second entangled particle responds accordingly by assigning it the opposite spin. This code ignores distance because the processor doesn't have to literally walk to a pixel on the screen and ask it to spin upside down, even if the screen is as big as the universe itself. And by the way, maybe the fact that we're all part of a computer simulation explains the Fermi paradox. We covered the Fermi paradox in another video. Check it out. The link is in the upper right corner. Could it be that we still haven't encountered other life forms simply because they are just not programmed into our simulation? However, this same assumption might suggest that they could be discovered at any moment. Who knows what the universe's game designers have programmed there after all? There's another astonishing phenomenon, this time not in the realm of physics, but society. In 2009, a self-proclaimed paranormal consultant, Fiona Broom, stumbled upon a rather peculiar fact. Contrary to her belief, the world-renowned human rights advocate Nelson Mandela had not died in prison during the 1980s. Instead, he had been released in 1990. and even managed to serve as the president of South Africa for several years. One might dismiss these assertions as mere fantasies of a paranormal consultant. However, Fiona Broome was so convinced that she distinctly remembered newspaper headlines announcing Mandela's death that she decided to conduct a full investigation. The results were mind-blowing. A surprising number of people, entirely unconnected to each other, also held the same belief. Many even claimed to remember Nelson Mandela's daughter's eulogy at his imagined funeral. The phenomenon took on a global scale when the politician eventually died in 2013. At that time, thousands of people around the world were taken aback by the news. Like Broome, they were under the impression that Mandela had died in prison during the 1980s. Fiona Broome named this phenomenon the Mandela effect. Yet, this was just the beginning of this very peculiar social phenomenon. With the rise of social networks, it quickly became evident that thousands of people from around the globe firmly believe in certain facts that aren't actually true, or their beliefs slightly, yet distinctively, deviate from reality. Let's consider some typical examples. This is what the logo of Volkswagen, the German automotive conglomerate, looks like. And here's how thousands of people remember this logo. Monopoly Man and his monocle. The Monopoly character wearing a top hat sports a monocle, but in fact, he doesn't. Jif, not Jiffy. People swear that there was a Jiffy peanut butter back in the day, but we speculate they're combining Jif with its competitor, Skippy, Pikachu's tail. Though many of us clearly remember black detailing on the Pokemon character's tail, in reality, it's just yellow. C-3PO has a silver leg. Even the biggest Star Wars fans get it wrong. The robot isn't all gold. He has one silver piece on his right leg. There are quite a few examples like this. The sheer number of people with identical false beliefs led proponents of the simulation hypothesis to tentatively propose that these might suggest the glitches in the software running our virtual universe. Of course, these assumptions may seem to lean heavily towards the realm of popular science fiction, but the wide incidence of the Mandela effect still urges us not to discard it entirely. Where did the idea that we are living in a simulation come from? And why do some people believe it is possible? The world's first truly working programmable computer, the ENIAC, performed about 5,000 operations per second in the 1940s. Today's fastest computer is the Frontier HPE Cray EX235. It computes at a speed of just over 1 exaflops. Here's what that number looks like. 1 quintillion operations per second. That is, today's most powerful computer is more powerful than the first one by a factor of 200 trillion. And it's been less than a century. If things continue moving at the same pace, then what? Even simple logic suggests that in the future, we'll be able to simulate entire universes. But if such a possibility exists, who knows? Maybe it's already happened. In 2003, Swedish philosopher and Oxford University professor Nick Bostrom published a serious scientific work with a simple and a little frightening title, Simulation Argument. We will try to explain in a simple way what the authoritative and globally recognized scientists came up with. So Nick Bostrom has 5 assumptions, and if all of them are true, then you, dear viewer, are probably living in a simulation. The first assumption: it is possible to simulate consciousness. This is a very important point. As you have noticed, all this time we have been skirting around the issue of consciousness. Let's suppose we've created a super complex simulation with exactly the same people as us running around. These bots, these NPCs, are also so sophisticated, let's say that they're capable of wondering if they're in the simulation. But wait, how can they think about anything? They're soulless programs. After all, you wouldn't think your smartphone could think or feel anything, would you? And it's much more real than a simulated character in a video game. In fact, this is too quick an assertion. Modern science defines consciousness, in brief, as the property of a complex system to reflect reality. That is, if something is complex enough, very, very complex, then it can have consciousness. And again, that's very briefly and simplistically. And we know such a highly complex system, the human brain. We know for sure, 100%, that this piece of organic matter can be a carrier of consciousness. But the brain is made up of just the same molecules and atoms that make up everything around us. Complex electrochemical reactions take place in it, and that's what we call thinking. But wait a minute, doesn't something very, very similar happen in modern computers? Do you see what this is about? We have not the slightest reason to believe that consciousness can appear only and exclusively in a jelly-like piece of organic matter. And if some microprocessor system would be endowed with the same complexity, there is not a single law of physics known to us that would deny the emergence of consciousness in such a system, or even more than one. That is, the conditional characters in a super mega complex simulation of the future may be as complex as the human brain, and there is no reason to believe that they could not develop some resemblance to our consciousness. Of course, that would require some enormous computational power. Gigantic. But recall the beginning of this video. How many times has the power of computers grown in just 80 years? 200 trillion times. And what if progress continues for another 80 years? Or 80,000, or 80 million. And here we come very close to Nick Bostrom's second assumption. The second assumption: the technological progress will not slow down in the foreseeable future. It's pretty clear. We assume that humanity will not hit an insurmountable barrier in its progress. Quite recently, such a barrier has loomed on the horizon, and futurologists got a bit discouraged. You've probably heard of Moore's Law. If you have not, let us summarize it briefly. It is not even a law, but an assumption based on observations formulated by Intel co-founder Gordon Moore. It states that the computational power of computers doubles about every 2 years. And it did happen that way with slight variations for decades. However, at a certain point, the law stopped working. The direct proportionality of Moore's Law began to decrease. Physical and technological limitations began to affect further growth of computational power. This trend became noticeable already in the early 2000s. Decreasing transistor sizes due to extreme limits, physical limitations in signal transmission, and increasing power consumption hindered further strict compliance with Moore's Law. Designing and manufacturing more powerful processors with high transistor densities became increasingly difficult and expensive. That's why futurologists became so despondent, and skeptics started talking about the very capacity limit that would be physically impossible to overcome. However, companies began to look for alternative ways to increase computational power, such as multi-core processors, optimization of algorithms, and development of specialized hardware solutions for specific tasks. Now, we are at an epochal turning point, when quantum computers are no longer a theory, but a reality. It is only a matter of their mass production and reduction of production cost. And quantum computers are not even something more powerful, but something fundamentally different. The physics working there is completely different. Who knows what else we will invent in a few generations, when quantum computers will become an ordinary thing? So we can be pretty sure that Nick Bostrom's assumption that computational power will not decrease is quite reasonable and justified. Okay, then what about the third assumption? The third assumption: advanced civilizations do not destroy themselves. Really, why should we care about technologies of the future if we simply will not get to this future because we will just die out? We will kill ourselves in a nuclear war or perish because of an asteroid impact, not being able to protect ourselves from it or settle on other planets. Well, it's even simpler here. If we put aside the elusive idea of the Great Filter, it is easy to understand that if we do manage to resettle on other planets, human civilization has all chances to become immortal. And as you know, Elon Musk, with his mission to Mars, is deliberately trying to help us do that. And he's making notable progress. One man, so far. We sincerely wish him luck. Let's move on. The fourth assumption: advanced civilizations want to run simulations. Indeed, as long as we ourselves are not such an advanced civilization, it is quite difficult for us to imagine why those advanced ones, would want to do this. Nick Bostrom has suggested that one reason might be historical simulation. People from an advanced civilization might want to see what their ancestors did, but instead of reading books, they play scenarios. Or we might be characters in a very advanced video game or something else. Who knows what those advanced ones might have in mind? After all, let's look at ourselves. The more we develop, the more we play video games and wander around the meta-universes. Why would this trend start to fade? Finally, the fifth assumption: if there are a lot of simulations, there's a good chance you're part of one of them. Well, that's it. Here we go. All 5 assumptions are working. There is no reason to disprove any of them. Are you getting a little uneasy? Here is what American astrophysicist and famous popularizer of science Neil deGrasse Tyson says about it. According to him, admitting the idea that it is possible to create a simulation within a simulation automatically means that we are likely to be in one of them. We take the computational power available to us today and realize that we have the ability to create an entire world in a computer. Now imagine a future where the power will be even greater and you can create characters who have free will. You set the laws by which this world lives. Now imagine that you are a character in this game. You think you have free will, and you decide that you want to invent the computer. And you do. Then you decide to create a world in your computer. You end up with a multitude of universes before you. You throw a dart. Which universe are you most likely to hit? The first universe? The real one, where it all began? Or the countless simulations that came after?
You look at our computing power today, and you say, I have the power to program a world inside of a computer. Well, imagine in the future where you have even more power than that, and you can create characters that have, for example, free will, or their own perception of free will. So this is a world, and I program in the laws that govern that world. That world will have its own laws of physics and chemistry and biology. Now you're a character in that world and you think you have free will, and you say, I want to invent a computer, so you do. Hey, I want to create a world in my computer. And then that world creates a world in its computer. And then you have simulations all the way down. So now you lay out all these universes and throw a dart. Which of these universes are you most likely to hit? The original one that started it, or the countless simulations, the daughter simulations that unfolded thereafter?
Elon Musk even goes much further and exaggerates it a bit. He says, we'd better hope we're in a simulation. We either create simulations indistinguishable from reality, or civilization will cease to exist. Those are our options. Elon believes that we are hardly living in a basic, real reality. Discussion of the simulation hypothesis sooner or later leads to the fact that statistically, it is really unlikely. Nick Bostrom is also certain. The chance that we are living in a simulation is very high. Meanwhile, Neil deGrasse Tyson reflects as follows, refining his earlier conclusions. If we haven't yet reached the technological stage of development to create our own realistic simulations, then either we're living in a main reality or we're living in the last simulated reality in the chain. This means the chances are 50-50. We're still on Musk's side, though. Of course, we've outlined things very simplistically here. In fact, it's much more complicated than that. The difficulty of finding a definite answer to the question of whether we are living in a simulation was outlined by philosopher David Chalmers. Any evidence in favor of a particular theory can be artificially simulated. That is, the hypothetical creators of our simulation can deliberately lead us down the path they want us to go. We can only hope that our current scientific theories aren't based on fake evidence, artificially fabricated by these very hypothetical creators. Think about the universe, from ancient times till now. The best human minds have been struggling to solve its mysteries. In ancient times, the Earth was considered as flat as a plate, resting either on 3 turtles or elephants, and the sky was seen as a bowl covering it. In ancient Greece, people already knew the Earth was round. However, the sun was thought to orbit our planet, not the other way around. Just think of how much the science progressed since those times. We know that we orbit the sun. Along with us, the sun orbits the center of the Milky Way galaxy. The Milky Way, with about 50 neighboring galaxies, revolve around an invisible gravity center in the local group of galaxies inside the Virgo supercluster. Like other superclusters, it turned out to be a part of the larger structure of the Laniakea supercluster, and its objects don't orbit around one point, but simply tend to collapse into a super heavy anomaly in the center called the Great Attractor. We can't see it because of the specific position of our galaxy. The disk of our galaxy blocks our view. But today, we aren't interested in the attractor, but in the frightening, empty area opposite it. Dipole repeller. Such empty areas in space are called voids. If you look at the universe from the side, it would appear as countless networks of galactic threads, separated by empty spaces called voids. This is what our world looks like if we represent it in one picture. Here, you can see 10 billion light-years of space, connected by galactic filaments. Here is your home. In terms of visual representation, the humanity has already literally reached the edge of the universe, marked by quasars. However, 2 dark spots have appeared in this phenomenal picture, showing the triumph of the human mind, and they spoiled everything. 2 dark mysteries of the universe. How are these threads of substance connected? The movement of planets, stars, and galaxies at great distances perfectly describes Newton's law of universal gravitation. Based on this movement, computer simulation showing the life of galaxies was created. It showed that weighing as much as they do, galaxies would no longer exist as a whole. Their stars would just scatter, but the fact that it hasn't happened means that something is holding them back. Next, astronomers measured the speed at which the stars lying at different distances from our galaxy's center orbited. It's easy to calculate this, knowing the mass and distance from the stars to the galaxy's center. But the researchers found the results quite surprising. The stars lying in the center of the galaxy and on its outskirts moved at the same speed, and they shouldn't. This means that either the physics of Newton and Einstein doesn't work, or the galaxy's outskirts are filled with some invisible substance. The scientists were quite puzzled and just exclaimed, "Amazing!" Their train of thought was rather simple. Only gravity can hold stars together. Gravity can only be created by mass. This means that in galaxies, there is some other additional mass holding the stars. And since this mass is not visible by telescopes, it simply cannot be seen. A brilliant thought. This invisible mass is called dark matter. With this in mind, scientists quickly created the standard cosmological model called lambda cold dark matter, abbreviated as lambda CDM. In other words, the standard cosmological model is a set of rules and equations that describes our universe and explains everything observed in it. In the modern standard cosmological model, the universe is filled with dark energy and cold dark matter, in addition to ordinary baryonic matter. According to this model, the age of the universe should be considered 13.799 plus or minus 0.021 billion years to be consistent with observations. Note that the term dark matter was adopted not because of this matter's invisibility. It would then be called invisible. Dark literally means dark, that is, incomprehensible. Nothing is known about this hypothetical substance. Well, except that it does not emit, reflect, or absorb light and other types of electromagnetic radiation. X-rays, radio waves, ultraviolet light pass through dark matter and don't interact with it in any way. Later on, scientists calculated that there is a lot of dark matter and energy in outer space. According to lambda CDM, our universe has only 5% of regular, so-called baryonic matter that forms all observable objects, 25% of dark matter registered due to gravity, and dark energy, which makes up as much as 70% of the total volume. It's believed that all dark matter appeared shortly after the Big Bang and spread in filaments throughout space. It was as if the World Wide Web had emerged, which pulled in the particles of the latter-formed visible substance due to the gravitational force. Once in the web, regular particles could no longer escape. Stars and planets formed from their clusters. And between the cells of this cosmic web, there emerged great empty spaces called voids. That is, vast chunks of space with no or almost no galaxies and clusters. Voids typically span across 10 to 100 megaparsecs or more, most commonly 30 to 350 million light-years. For example, the Boötes void in the Boötes constellation spans across 330 million light-years. By the way, we've made a video about it. Be sure to watch it. The threads in the cosmic web are distributed unevenly. Somewhere there are almost none of them, but somewhere they are huddled together. For example, dark matter is virtually absent in the strange Dragonfly 44 galaxy from the Cetus constellation. But the other galaxy, from the Coma Berenices cluster, is 99.9% dark matter. Scientists are yet to discover what dark secrets are hidden in this invisible wonderland. But they found that our Milky Way is merely a bug compared to a ghost galaxy. It contains twice as much dark matter as ordinary matter. Most recently, scientists managed to draw up a detailed map of how dark matter is distributed over a large area of the southern sky. The map was created by astronomers at the Inter-American Observatory in Chile after analyzing images of 226 million galaxies. Just look at it. Isn't it breathtaking? A real space show where dark matter is highlighted in bright purple. But what is the nature of this invisible matter highlighted as purple on the map? Of course, the first thing that comes to mind is its connection with antimatter. Let me explain right away. they have nothing in common. When reacting with regular baryonic matter, antimatter annihilates. It turns mainly into light, that is, the pure form of energy. Visually, it looks like an explosion. And since Einstein proved that energy is matter multiplied by the speed of light squared, and the speed of light is no less than 3 × 108 meters per second, then a lot of energy will be released. For example, the energy of 1 milligram of antimatter is enough to fly to Mars, and that's only 1 milligram. This is 1,000th of a gram of a substance. But where did this dark matter come from? At first, scientists suggested that the nature of invisible matter is connected to a massive astrophysical compact halo object called macho. Since machos are not bright objects, they are difficult to detect. They come in many varieties. These are black holes, neutron stars, brown dwarfs, or orphan planets. Sometimes white dwarfs, and very dim red dwarfs are classified as machos. Among all of these, primary black holes are especially intriguing. They formed shortly after the Big Bang and settled on the outskirts of galaxies. There are such space objects in our Milky Way. They are real monsters, devouring all matter and even light on their way. The substance inside of them is compressed with incredible density. If the Earth was compressed so tightly, it would be the size of a peanut. All of these supermassive objects bend light with their gravitational force. Look at an object through a glass. Can you see that the image is distorted? Almost the same effects would be observed in the space area rich in black holes. However, astronomers don't observe any distortions. So machos are no longer seen as the main dark matter sources. And to be honest, this explanation would be too trivial, but the universe likes to throw very tricky puzzles. After that, scientists turned to the quantum world. They were interested in weakly interacting particles, which are heavier than regular ones. There were none among those known to science. But that doesn't mean they don't exist at all. Weakly interacting massive particles, or WIMPs for short, are now considered to be a potential dark matter source. It's worth noting right away that WIMPs haven't yet been discovered. As of now, they exist only in theory. But if scientists' conclusions are correct, then WIMPs have several varieties named after some well-known particles: photino, gravitino, neutralino, etc. The real hunt is on. Scientists were trying to catch WIMPs both in cosmic rays and in a purely terrestrial device, the Hadron Collider. Giant detectors are being built to search for WIMPs in cosmic rays. They are huge water tanks, hundreds of cubic meters deep, hidden at a depth of about 1 kilometer, preferably under rock. This is done to cut off other particles that can't break through a kilometer of rock. For WIMPs, this isn't as much of a hindrance. There are 2 ways in which such detectors look for WIMPs. The first way is to try to detect WIMPs directly. The second is to detect WIMP-generated neutrinos. Scientists have suggested that the Sun captures WIMP particles when moving through space, but it doesn't release them back due to its huge mass. Because of this, WIMP concentration inside our star is constantly growing. These particles become very crowded, especially in the center of the star. They begin to collide with each other and turn into, you guessed it, neutrinos. So what, you can say? Countless nuclear reactions accompanied by the formation of neutrinos occur inside the Sun all the time. And such neutrinos were already discovered back in 1956. But neutrinos can be very different. The neutrinos formed as a result of WIMP collision have dozens of times more energy than the already well-known regular solar neutrinos. These energy-rich neutrinos are what scientists are trying to catch under 1 kilometer of rock. But so far, neither WIMP itself nor the WIMP-generated neutrinos have been found. Scientists are very hopeful about X-mass detector, which is being created in Japan. A water reservoir with a volume of almost 800 cubic meters is hidden under the rock at a depth of the same 1,000 meters. It contains a target in the form of a container filled with liquid xenon. If a WIMP hits a xenon nucleus, it will cause a flash and the nucleus will release a photon. It will definitely be seen by at least one of the 642 special photoelectric sensors. X-mass is calculated to be 100 times more sensitive than existing WIMP particle detectors. In addition, if this hundreds of tons detector gets triggered, the particle will be registered directly and not indirectly, as when discovering an energetic neutrino. After all, you never know how it could be formed. There is a more interesting hypothesis that the invisible part of the universe can be produced not by one WIMP particle, but by a whole world of particles, mirroring ours. When you think about it, if ordinary matter is made up of a lot of different ingredients, why can't dark matter be as complex? Think about it. Dark protons, dark electrons, dark photons. Suppose you are sitting on a cozy sofa and watching our video with a friend. Suddenly, all the matter in his body becomes dark for some reason. What will you see? Nothing. The electromagnetic force that binds atoms and molecules, cells, and organs into a single whole will disappear from the body. So your friend will sort of evaporate in an instant. The dark matter making up his body will simply scatter in all directions. Then the second part of the horror will come, but you won't notice it either. Pieces of your body will keep coming back. The speed of their movement won't be enough to overcome the planet's gravity, and the particles will remain attached to the Earth. Without the electromagnetic force preventing the passage of dark matter through the planet, they would just fly back and forth and return to the starting point about every 90 minutes. Since we are constantly moving in a large spaceship called Earth around our galaxy's center, billions of particles collide with our body, but only hundreds of thousands of them a year manage to collide with the nuclei of our atoms. As a result, it turns out that everyone interacts with dark matter about 10 to 11 times per hour. Experiments aiming to find dark particles are also conducted at the Large Hadron Collider. Scientists try to get WIMPs when colliding ordinary particles accelerated to super speed. A lot of quantum garbage remains as a result of these experiments. As in any landfill, sometimes you can stumble upon a real treasure. One time, researchers managed to unearth the famous Higgs boson there. But so far, WIMPs haven't been found. However, scientists hope to conduct more successful experiments at the New Generation Large Hadron Collider, spanning across a whopping 100 kilometers, being built under Lake Geneva. It will be 4 times longer and 10 times more powerful than the current one. But dark matter is not the only wild card in our structured universe. Remember how we said at the start of the video that the standard model of cosmology suggests that the universe is 25% dark matter and 70% dark energy? That is, there is almost 3 times more dark energy. So if dark matter is a wild card, then dark energy is like a wild deck of cards. Well, let's try to take a closer look at this deck. These two dark components of our world are not related in any way. Dark energy doesn't form clots that can serve as building materials for stars and planets. Unlike dark matter, it's evenly distributed throughout the universe. There are as much of it in galaxies and clusters of galaxies as outside of them. In addition, dark matter has mass and bends space with its gravity, and dark energy experiences anti-gravity. It is sewn into every empty slot in our space web, that is, into space itself, and constantly expands as if adding cubes of space it consists of, adding them one by one. Ultimately, this is what causes the universe to accelerate, if in fact there is an entity with such properties. But what does it mean that the universe accelerates? First of all, the universe expands. Edwin Hubble proved that distant galaxies are drifting even farther away at the speed which is directionally proportional to how far a particular galaxy is. Second, the concept of acceleration means that if you measured the speed of one of these galaxies and visited it in 1 billion years to make the second measurement, you would find that it has increased. Galaxies are becoming more and more distant at an ever-increasing speed. In the time following the Big Bang, dark energy spread at an insane speed and rapidly expanded the universe. Now, it's no longer as strong, but still, it's capable of doubling the scope of the universe in 10 billion years. At the same time, the density of dark energy accelerating it in all directions is extremely low. So far, vacuum is considered as the most probable dark energy source. Its energy density doesn't change as the universe expands, which is consistent with negative pressure. Another rival is a hypothetical super-weak field called the quintessence. Scientists hope to better clarify the nature of dark energy, first and foremost with the help of new astronomical observations. Meanwhile, researchers are creating many new hypotheses explaining it. One of them is just a gift to those who predict apocalypse. Its authors are astrophysicists from the Swinburne University of Technology in Australia and the University of Portsmouth in the UK. They believe that dark energy can rip our world apart. Over time, this dark force will begin to surpass all others in the universe. As a result, gravitationally bound structures will be ripped apart, and electrostatic and intranuclear bonds will be destroyed. Microparticles will decay, and the world will eventually come to a ruin. Or maybe some cosmic catastrophe will lead to critical fluctuations in dark energy. Then the universe will collapse into a singularity. The only good news here is that dark energy will not end the world as we know it in the foreseeable future. According to scientists, this can happen when the universe is 1,000 times older than it is now. This gives us enough time to thoroughly study dark matter, dark energy, and tame them to prevent any catastrophe. Do you agree? Will we ever fully understand the next mysterious object? One of the many enigmas that perplex astronomers? Some speculate that it's a dump for nuclear waste. But is it really? In the Centaur constellation, there's a star system of Alpha Centauri, which consists of 3 stars. Inside of this southern constellation lies something truly remarkable: Przybylski's star. It weighs 4 times the mass of the Sun and is 365 light-years from Earth. Regular stars resemble thermonuclear engines which synthesize heavier elements inside their nucleus. But Przybylski's star creates elements that aren't typically found in stars or elements yet to be discovered. In this video, you will learn what makes the Przybylski star so unique. Are there any elements that we haven't discovered yet? Can extraterrestrial civilizations use this star as a radioactive waste disposal site? The mystery of Przybylski's star. Scientific explanation or traces of extraterrestrial civilizations. Subscribe to our channel to see all our content and watch the next episodes even sooner. HD 101065, or the Przybylski star, but we might as well call it plutonium, because it seems to have a lot of plutonium, as well as other super heavy elements which are simultaneously unstable and very short-living. However, these elements shouldn't be there, and their presence can be explained by one of these options. First, there are some elements which we didn't expect to find in nature. Second, postulating the existence of super heavy elements is a mistake to begin with. Or third, aliens created artificial elements and dumped them into this star. Let's find out which one it is. Do you know what makes this object so unique? Its highly unique spectrum. Everyone who has seen it claims it was one of the weirdest star spectrums they have ever come across. A spectrum reveals which elements a star contains. The stumbling block for the researchers was that they couldn't get comprehensive data on how many elements it contains. Some scientists talk about an infinite number of lines, which makes them impossible to study in detail. How can this be? Astronomers have studied the Przybylski star since the 1960s, but to this day, they have no idea what elements it consists of. One theory suggests this might be because it contains elements and isotopes scientists have never discovered in nature. The data was obtained using one of the methods which connects the type of light emitted by a star with elements it contains. The results made scientists realize their previous conclusions concerning the contents of HD 101065 were inconsistent. First, it appears from the spectrum that it contains almost no iron, which is very strange by itself. Most stars survive by fusing lighter elements with heavier ones, and these fusions often result in iron or some other elements. Second, this star is rich in lanthanides, even heavier elements such as holmium and europium, which are present in lesser quantities in common stars. At the same time, Professor Przybylski has suggested that this star has existed long enough to create a lot of heavy elements. According to several studies, this star also contains atoms that are not supposed to be there. In particular, atoms of promethium and plutonium. These elements and their isotopes have a relatively short half-life, a period it takes half the atoms of a radioactive substance to decompose. For example, promethium has a half-life period of less than 20 years. Plutonium has a maximum half-life period of about 24,000 years, which is a relatively small number for a star. This means that if those elements aren't new compositions, or they aren't being replenished, they should have completely decomposed by the time when people appeared and learned how to use telescopes. So far, there are several possible explanations. Astronomers argue that these atoms could have appeared as a result of creating a supernova, or current reactions catalyzed by a neutron star close by. Unfortunately, very little data support these theories. However, there might exist another possible explanation which has nothing to do with the latter. Przybylski's star might contain some super heavy elements and isotopes which haven't been discovered yet. After some time, these super heavy atoms can break down into short-living isotopes that we can observe. In particular, these atoms can belong to the following three elements: flerovium, unbehexium, or unbenylium. Scientists have managed to create as few as 100 atoms of flerovium in the laboratory setting. As for unbehexium and unbenylium, they exist only in theory. We haven't yet discovered any of these elements in nature. If the described theory is correct, studying Przybylski's star will enable us to explore these elements in real life. There is a slight chance that isotopes inside this heavenly body are a part of the so-called stability island, a hypothetical group of super heavy and super stable elements which have long been pursued by scientists. But today, it's clear that everything is not that easy. Thanks to the scientific findings, we know that Przybylski's star belongs to a special type of app stars, or chemically peculiar A stars. As a rule, regular A-type stars are hot and don't have a magnetic field. But app stars are cold on the surface. They have a strong magnetic field and quite long rotation periods. For some reason, these stars contain lots of lanthanides and little iron. So this means the Przybylski star is not that unique after all. As if strange chemical composition wasn't enough, Przybylski star is noted for its unusual movement pattern. A new analysis led by researchers from the Leibniz Institute for Astrophysics, Potsdam in Germany, has discovered that HD 101065 isn't just composed of bizarre stuff. It also exhibits bizarre movement. And a team from Chile discovered that the star's rotation period stretches out over 188 years. Our analysis of newly acquired and historic longitudinal magnetic field measurements indicates that Przybylski star is also unusual with respect to its extremely slow rotation, the researchers state. That's a pretty long time for a star to do a 360, although slow rotation could be considered normal for app stars, as I mentioned earlier. There is a chance that we've misinterpreted some information, which means that the Przybylski star doesn't contain short-living isotopes. After all, this star's spectrum is difficult to identify. Spectrums usually have several relatively clear lines that correspond to various elements. But when it comes to this star, such lines occur almost everywhere. This has sparked a lively discussion as to what goes on, which continues even today. There is a questionable but quite popular theory which suggests that the star's composition resembles the products of artificial nuclear fission. Back in 1980, American scientists Daniel Whitmire and Jason Wright suggested that extraterrestrial civilizations can use their stars to store nuclear waste. They even pointed out that Type A stars, such as Przybylski's star, are most probably where this waste can be found. Such short-living, apparently artificial elements in A-type stars can be really seen as evidence of an artifact of a well-known SETI program. Rest assured, we will find an answer to the question of how these elements appeared on this star. Nonetheless, we should keep on trying to reveal this mystery, because even if a SETI artifact won't find the evidence of the existence of extraterrestrial civilization, these findings will be of great interest to the scientists. Quite recently, scientists came up with a hypothesis that can explain the anomalous chemical contents of the star. It is based on the fact that a neutron star influences the atmosphere of Przybylski's star, with which it makes up a closely linked system. Theoretically speaking, this hypothesis can be feasible. However, there's a big caveat. There are no neutron stars around. Indeed, scientists from the University of South Wales hypothesize that actinides in Przybylski's star can be the evidence of slow degradation of super-heavy elements. The theory posits the existence of a so-called stability island that includes elements with a nucleus containing 114 or more protons. These are super-heavy elements, but at the same time, they are long-living. If we hypothesize the existence of such elements, then short-living plutonium, einsteinium, and other elements found on this star will simply be degradation products. In other words, we can discover a new isotope obtained as an element that exists in nature. Don't be surprised, there is nothing special. For example, helium was first found on the Sun. I think we all agree that Przybylski's star's unique properties will remain a mystery for many scientists all around the world well into the future. Perhaps someone will help us solve this problem right now. Can someone travel back from the future and tell us the secret of Przybylski's star? What would happen if you went back in time and killed your own grandfather? Or, in an alternative past, met your young mom and became your own father? Sounds crazy, doesn't it? But what if we say that not just well-known scientists, but even Nobel laureates are scratching their heads over such paradoxes? What for? Is time travel impossible? Not everything is clear, which makes the paradoxes even more interesting. Today, we'll talk about the most mind-blowing time travel paradoxes. The paradoxes of time travel. The Grandpa Paradox. Let's start with the famous grandfather paradox. By the way, this is the real term, and it's also called the murdered grandfather paradox. But we'll omit the murdering part for the sake of being family-friendly. Imagine that you are the grandson of a man who stood at the origins of an entire dynasty, which eventually caused the deaths of millions of people, or even destroyed the world. Having received a unique opportunity to use the time machine, you go into the past with one goal: to do anything to prevent your grandparents from meeting and passing their genes to the next generations. You rightfully think that in this way, you will eliminate the entire family line, and the world will become a better place. The reason for the paradox is obvious. In this case, you won't be born, but you have already been born because here you are, flesh, bones, and everything. Both regular daydreamers and great thinkers have tried to solve this paradox. It basically boiled down to the fact that every time you try to change the course of history, there will always be something that gets in your way. Or history will follow the same path anyway, with only slight variations. So, for example, scientists describe one of the grandfather paradox scenarios. Say if you could go back in time and do something with Hitler when he was still young, then the atrocious Second World War would not have happened. This assumption is countered by many by the fact that instead of Hitler, there would be another dictator who would bring no less terrible things. Although the grandfather paradox is the most famous one, it is only a small piece in a great tapestry of paradoxes which are called the time travel paradoxes. And now you'll get to know what they are. The predestination paradox. This is a spin on the grandfather paradox, but it's even more interesting. A paradox occurs when the time traveler's actions become part of past events and eventually lead to the event he is trying to prevent. This leads to a temporal cycle of casualty in which event 1 in the past influences event 2 in the future. Time travel to the past, which in turn triggers event 1. This creates a cycle of events that makes it impossible for the time traveler to change history, and any attempts to prevent something in the past will simply result in causing the event instead of preempting it. This paradox suggests that things are destined to happen because they have already happened once, and no matter what happens, the outcome will always be the same. Does it sound confusing? Let me give you an example. Imagine that your friend dies in a car accident, and you return to that terrible day to save him from an unfortunate fate. You hurry to the car accident site only to realize that you knocked down some passerby by accident. You are horrified to discover that it was in fact your friend. And you are that very same absent-minded driver. Your very attempt to change the past leads to the predestination paradox. The scenario of events that you have experienced is already built into the general vision of reality, and by trying to change the past, you will only complete your role in bringing about some event in history without changing it. This paradox implies not only your immediate role, for example, the role of that driver. Predestination arises from the very fact of you traveling into the past. This is clearly shown in the 2002 film Time Machine. Guy Pearce's character, Dr. Alexander Hartigan, witnesses his fiancée being killed by a robber. This tragic episode prompts him to construct a time machine in order to go back to the past and save her from death. However, the subsequent attempts to fix things led the doctor to the sad conclusion: I could come back 1,000 times and see her die 1,000 ways. Having then traveled many centuries into the future to find out if this problem would be solved, Hartigan heard these words from a mystical being: You built your time machine because of Emma's death. If she had lived, it would never have existed. So how could you use your machine to go back and save her? You are the inescapable result of your tragedy. The bootstrap paradox. The previous paradoxes illustrate the unalterability of past events. Now we'll explain a similar scenario, but with feedback, the so-called bootstrap paradox. This is a paradox where an object, a person, an inanimate object, or information that was sent back in time creates an endless loop. In this cycle, the given object doesn't have a clear, traceable origin. It's not clear where it came from in the first place. This is because altered past events begin to affect the object in the initial time. Thus, its origins seem to blur between these two moments in history. Imagine that you are a 20-year-old time traveler. You travel 21 years back in time, meet a girl, and start a passionate affair. After a couple of months, you return to your time, not suspecting that you got the girl pregnant. Her child in her time grows up to become a 20-year-old time traveler who goes back 21 years, and so on. The paradox repeatedly pops up in literature and cinema. In 1959, American science fiction writer Robert Heinlein wrote his classic short story, You Are All Zombies, on this subject. And thanks to the Terminator, 2 generations have known this paradox. This incident is also known as the ontological paradox, because ontology is a branch of philosophy that studies the nature of being and existence. Such ontological paradoxes imply that the future, present, and past aren't set in stone, and this poses a difficult problem for scientists. How to reliably establish the origin of something if there is a chance that it will get to us from the future? And there really is such a possibility, since Einstein's equations deem closed time loops possible. The physicist and Nobel laureate Kip Thorne became the first scientist to prove that the so-called wormholes, that is, portals to the past, can be theoretically created under certain conditions. Once again, time travel does not violate the laws of physics. So, the time traveler paradoxes require a solution. And this need becomes especially evident when such paradoxes meet experimental physics. The Polchinski's paradox. Joseph Polchinski, an American theoretical physicist, proposed a time paradox scenario in which a billiard ball is fired into a curved wormhole. Let us remind you that a wormhole is viewed by theoretical physicists as a conceptual structure that connects two separate points in space-time. A curved wormhole in the Polchinski's paradox serves as a kind of time portal. The entry and exit points are located very closely from each other, but are separated by time. And so, the ball flies out from the other side of the wormhole in the past just in time to hit its younger version, repel it, and thereby prevent it from entering the portal. The Polchinski's paradox is an elegant and simple generalization of the time travel issues at the macroscopic level. He smartly bypasses the issues of free will, grandfathers, little Hitlers, quantum superposition, and a host of other problems that only prevent theoretical scientists from understanding these puzzling things. The idea is based on the laws of motion, doesn't refer to shaky speculations, and therefore represents the best way to study time paradoxes. The question is, how will it work? And will it work at all? And if not, why not if it should? This paradox was taken seriously by very respectable physicists. For example, Kip Thorne is a well-known scientist who has discussed it in detail in his book, Black Holes and Time Distortions. Thorne and other colleagues analyzed different scenarios of this experiment. He couldn't do without quantum physics. for how to proceed without it. So scientists have come to the conclusion that although Polchinski's speculative installation may yield different results each time, the chance of a non-paradoxical result is quite high. That is, it's likely that each time the ball will fly out of the wormhole in a way that doesn't prevent its earlier version from getting into the wormhole in the first place. And now, let's go back to the grandfather's paradox that was mentioned early on in this video. Remember we said that something always prevents us from dramatically changing the course of events? Turns out, speculative conclusions are very similar to the findings of respectable physicists after all. Of course, we don't claim that everything is predetermined. We're just trying to be on the same page with Kip Thorne to unravel these mind-boggling puzzles. Are we destined to find other civilizations? Will we ever obtain evidence of their existence? Or perhaps we already have. For many decades, mankind has been trying to find even the smallest sign suggesting the existence of an extraterrestrial civilization. We observe space around the clock using the most advanced telescopes. With bated breath, we listen to the barely perceptible rustles in pitch darkness. Space responds to us only with the soulless chirping of pulsars and the white noise of the cosmic microwave background radiation. But one day, on August 15th, 1977, we did get a signal. It was so powerful and like nothing else before that it was just wow. And this signal has been haunting scientists, space enthusiasts, and simply dreamers for half a century. The WOW signal. Full history and explanation. In 1977, the SETI, Search for Extraterrestrial Intelligence program, was in full swing. Humanity was still full of optimism and enthusiasm in trying to discover signs that extraterrestrial intelligent civilization exists. The SETI program is directly funded by NASA itself. The Big Ear radio telescope has been listening to space noise day after day for many consecutive months. Scientists and enthusiasts were scrupulously trying to find something unusual in the received data. For a long time, the space responded with almost nothing but silence. All of a sudden, the silence was briefly broken on August 15, 1977. Dr. Jerry Eyman registered what all enthusiasts have been looking forward to: a sharp, powerful radio signal from space that was fully consistent with the theorists' expectations of extraterrestrial contacts. It stood out so strongly against the background of the usual cosmic white noise that Dr. Eyman excitedly circled the encoded signal recording in red ink. He uttered this very exclamation, which immediately became the permanent name of the signal itself and the event in general. Until now, many seriously think that WOW is the deciphered meaning of the alien message. In fact, if Dr. Eyman had been a little less restrained in choosing his words, he could have written anything, even WTF, and then the signal would have been called the WTF signal. But don't let this little revelation disappoint you. The signal actually came from outer space, specifically from the Sagittarius constellation. There's no doubt about it. The audio that allegedly represents this very signal is widely shared on the internet. The fact that it went viral simply obliges us to play the recording. Are you ready? Let's hear it. We don't need to point out to you that fans of extraterrestrial civilizations, and especially skeptics, have broken the audio into pieces and analyzed every bit. Everyone wanted to confirm or deny its authenticity and extraterrestrial origin. And for the very first impressive results, neither a supercomputer, nor neural networks, nor symposium of experts were needed. It was enough just to speed up the recording. Get ready. This can sound frightening. What is this? Is it trying to communicate with us? Is this a greeting? Or maybe a threat? Did these sounds inspire Ridley Scott when he created the engineers' voices in Alien Covenant? Let's do the same thing that picky enthusiasts did a long time ago. Let's slow down the recording even more. Somehow, it doesn't sound scary at all. In fact, it's very earthly, isn't it? It's difficult to make out the voice, but it's possible. It says in English, "We lost him at 7 p.m. We've got a 1061. What is 1061? This isn't hard to figure out with basic Googling skills. It's simple. This is a police code that means stopping a suspicious car. Yes, pranksters or hype seekers just took a random recording of police negotiations and slowed it down several times. The usual simple fake. Well, it's either that or aliens from a distant planet also speak English. And even now, it doesn't disappoint us. After all, the signal itself is definitely not fake. Okay, then what does the signal actually sound like? After all, is there a real record? No. The Big Ear telescope didn't record any sounds at all. Its task in the study was only to record the signal strength. That is, this mumbo-jumbo circled by the scientist is all we have. But this doesn't negate the value of this data and the unique nature of the event. And now, we need to figure out what this unique phenomenon is. First, we need to understand what the Big Ear actually heard that day. Let's look again at that same historical document. All these numbers on paper are signal strength designations. As you can see, everywhere there are mostly numbers and small ones, 1s, 2s, or just blanks. And the WOW signals code looks like your Facebook password or something that a cat typed when walking on a keyboard. The fact is that the radio telescope encoded the signal strength into numbers from 1 to 9, and if the power was greater, it used an alphabetical series from A to Z. Remember we said that the radio telescope listened mostly to white noise? These are the very 1s, 2s, less often 3s. Space is intensity less than 1. 6 or 7 was something out of the ordinary. That special attention was also paid to such bursts. Dr. Iman circled even them. And now imagine that against the background of these weak signals, which have already become familiar over the months of observation, the Big Ear suddenly registers this. There was barely enough alphabet here to display the strength of the received signal. It turned out to be 30 times more powerful than what the radio telescope had heard for a long time before. This was the first time such a thing had been registered. And now, to make it clear, it is worth noting what the Big Ear radio telescope was like at that time. In general, when it comes to radio telescopes, we imagine something like this: a huge, impressive antenna looking into space against the backdrop of a beautiful sky. And basically, radio telescopes are just that. But not only wasn't the Big Ear that aesthetic, but it lacked some of this functionality. Here's what it looked like. More like a football field, giving an impression of something unfinished. The question is, how did it turn to observe not one point of the starry sky, but other areas? The answer is simple. it didn't. It rotated along with the rotation of the Earth around its axis. That is, it could observe the same part of the sky only once a day for 72 seconds. That's why the signal is exactly 72 seconds long. And here too, the dynamics is clearly visible as you move. For the first 36 seconds, the signal grows louder, reaching an incredible peak, and fades out during the last 36 seconds. The way the signal was detected is by no means the same as in the film Contact. Dr. Iman didn't watch the equipment day and night, but noticed the surge only after it happened. But even if he registered the signal here and now, the next communication session would happen the next day. And so it all happened a day later, and then more than once, the research team tried to detect this signal again. Other radio telescope teams joined in this big hunt, and they immediately deployed antennas to that very part of the sky. But the unknown source of the signal had already disappeared. Scientists have been trying to register this signal again for years. Unfortunately, it didn't bring any results. What is so special about the WOW signal that it has excited everyone for so many years? The fact is that it's almost impossible to explain its earthly origin. This impossibility lies in the most fundamental moment, the frequency at which the signal was received. This frequency is 1,420 megahertz, and terrestrial communications are forbidden to use it. To soften the word forbidden, let's say its use is reserved for the study of extraterrestrial signals. The point is as follows. Let's say we want to pick up a signal from aliens. It was impossible in 1977 to listen to the entire radio range for this. No power would be enough. Physicists Bernard Oliver, Giuseppe Cocconi, and Philip Morrison proposed a rather elegant solution back in 1959, at least an intermediate solution. It comes down to this. By definition, we have no idea about the frequency that hypothetical aliens can transmit something, whether they transmit anything, or even if they exist at all. And if so, then we are free to make any assumptions. Oliver, Cocconi, and Morrison were convinced that 1,420 megahertz was the most suitable frequency for interstellar communication. This is because hydrogen, the most common element in the universe, emits at this frequency. Here, we simplify a lot of things to avoid subtle and obscure details. In fact, there were many reasons put forward for such an assumption that were quite logical and scientific. And then, if we came to this, then why not assume that other intelligent civilizations would make similar assumptions? In any case, we still have no other options than to speculate and reason. The physicists' idea turned out to be quite convincing, and the frequency of 1,420 megahertz was reserved for space research. It's not used by terrestrial means of communication to avoid interference. Now it serves as a hope for those who want to find aliens. It seemed that our hopes would finally come to fruition, but alas. At first, Iman himself and his colleagues made several attempts to restore and identify the signal. Dr. Iman's team spent several months trying to pick up a signal at the same area. Nothing. 10 years later, astronomer Robert Gray decided to revisit the issue. In 1987 and 1989, he used the meta-array at the Oak Ridge Observatory. Still nothing. In July 1995, SETI League Executive Director Paul Shook made his contribution to the desperate quest. While testing the signal detection software for the Argus project, he made several observations of the WOW. Shook used a 12-meter radio telescope at the National Radio Astronomy Observatory in Green Bank, West Virginia. But this also didn't bring any result. In 1995 and 1996, Robert Gray also revisited the issue. He went all in and used the Very Large Array, which is much more sensitive than the Big Ear. Astronomers Gray and Simon Ellingson later looked for a repeated event in 1999 using a 26-meter radio telescope at the University of Tasmania's Mount Pleasant Radio Observatory. 6 14-hour sightings were made from nearby positions, but nothing like a WOW signal was ever detected. We aren't just talking about continuous failures of the WOW signal redetection. Each of them consolidated the skeptic's viewpoint. For a long time, skeptics couldn't form a convincing hypothesis explaining the signal's origin. And only in 2017, half a century after the first and last time the signal was detected, such a hypothesis emerged. Antonio Paris, assistant professor of astronomy and astrophysics from St. Petersburg College in Florida, has suggested that the hydrogen clouds surrounding 2 comets, 266P Christensen and 335P Gibbs, could be the WOW source. About 200 studies were conducted from November 27, 2016 to February 24, 2017. They showed that the Christensen comet really makes some noise coming towards the Earth with a similar frequency signal. Almost identical studies were conducted on other known comets, and the results were also similar. Indeed, comets spreading a hydrogen cloud over millions of kilometers around create this kind of effect. It would seem that all hopes have collapsed, and all the magic of the WOW crumbled in the face of boring facts, as always. But many astronomers still reject Paris's theory, also citing quite convincing evidence for its unsoundness. There are indeed many inconsistencies, but no alternatives could be found. There were no new signals, and there was nothing in that part of the sky that could even remotely be considered a potential source of radio signals. This was the case until 2020. Hope was reborn from the ashes when a simple amateur astronomer, Alberto Caballero, published the results of his own research. When studying the area of the sky where the WOW signal was detected, Caballero discovered as many as 15 stars that could hypothetically be the source of the mysterious radio signal. Alberto introduced 2 assumptions. First, he suggested that the radio signal came from an Earth-like exoplanet. This planet, like the Earth, revolves around a sun-like star. The second assumption was derived from the Drake equation. According to it, the planet could be no closer than 500 light-years from the Sun. To compile a list of hypothetical signal sources, the astronomer turned to the Gaia telescope database. The data contained information about the properties and position of the stars in the Milky Way. He selected 66G and K-type stars, which were located in 2 areas in the Sagittarius constellation. Caballero was looking for stars with a radius of 0.83 to 1.15 solar radii. It turned out that only 1 star fits this criteria. The catalog designates this star as 2MASS 1928 1982-264-0123. It lies 1,801 light-years from us. Its characteristics are slightly shocking when considering how perfectly it matches the parameters of our native star. Radius is 0.996 of the Sun's radius. Luminosity is 1.0007 of that of the Sun. The temperature is 5,783 Kelvin. Well, isn't that the twin brother of the Sun? Another 14 Sun-like stars with estimated temperatures between 5,730 and 5,830 Kelvin are also located in the region where the signal came from. However, there's not enough information about their luminosity and radius to conduct the research. But one was enough to revive interest in the topic. Since Alberto Caballero's discovery, there haven't been further breakthroughs in pursuit of the WOW signal source, but the topic itself has gained a second wind. And perhaps thanks to new data, humanity will still be able to catch that very elusive signal. Or some other, it doesn't matter. And when this happens, we are waiting for civilizational scale discoveries. Just recently, humanity became captivated not by a signal, but by probably the very object we were looking for among the countless celestial bodies. The solar system is literally swarming with comets and asteroids of various sizes and trajectories. We discover more and more of them every night, dozens or even hundreds of them. For astronomers, this has long been a boring routine. But October 19th, 2017 was anything but boring. That night deprived astronomers around the world of normal sleep and the rest of their nerves for a long time. It made them drop everything and deploy all telescopes. Even the orbiting observatories, Spitzer and the legendary Hubble, were instructed to urgently turn around and look at one point, to the point where something was flying that would later be called Oumuamua. It means messenger from afar or scout in Hawaiian. Why? In this video, we will tell you about one of the most mysterious space objects in history. Perhaps we've never been closer to solving Fermi's paradox and solving the mystery of whether we're alone in the universe. Oumuamua, solution to the Fermi paradox? However, it is worth starting with the fact that at first, nothing particularly unusual was found in it, and it was discovered not even by humans, but by robots. The fact is that most of the routine work in human space observation has long been done by automated systems. There are several such robotic telescopes operating on Earth now, and they are the first to detect something fast-moving. If something is moving fast, it means it's not some distant star, but an object somewhere here, flickering right beside us. Usually, those are either asteroids or comets. This work is ongoing, and detections occur almost every night. To date, more than 1 million asteroids in our system have already been detected. Divide that by 20 to 30 years of active observations, and it turns out that we discover 100 to 150 new objects every night. It's been a regular thing for a long time. Now, another seemingly ordinary object has been found. It was discovered by the Pan-STARRS robotic telescope in Hawaii. It's a rather large device, 2 meters in diameter. And at first, this discovery wasn't of much interest. Just another flying thing in the night sky. At first sight, it looked like a comet. The orbit is elongated, almost parabolic. But then the previous observations were brought up. Usually, this is how it happens. We see something, then we open the archives of yesterday and the day before and see something faintly visible in the same place or next to it. And then it is clear that this is the same object, and we just overlooked it, didn't notice it last night. So, having collected measurements for several consecutive nights and having looked at what has turned out, everybody was astonished. And its orbit is hyperbolic. In other words, it will just fly close to the sun, and the sun will only be able to change its trajectory slightly, not capture it so that it becomes a satellite, since this something is flying at a very high speed. Nothing in our solar system flies at that speed. Usually, objects do not fly at such high speeds and either fall directly onto the sun or become its eternal satellites. It became obvious that we were dealing with something extremely unusual. What's so unusual about it? Well, everything. Almost everything. But first things first. This was the first time in the history of science that an object had been discovered flying into the solar system from unknown origins. This fact alone makes it not just unusual, but sensational. Until now, everything that was found, all these million-plus bodies, were our native. These asteroids, comets, and satellites have all been around for billions of years. And then suddenly, one flew in from somewhere outside. Basically, that's to be expected. After all, other stars also have their own planets, their own comets, and probably their own analogs of the Kuiper Belt and the Oort cloud. They may well be losing something, just as we are. This is all true, but that's often the case with many discoveries. We could have expected it, but we didn't, and it came. At first, it wasn't clear what it was like, but gradually we found out. And how did we find it out? Everyone was watching it. All large telescopes, even Hubble and Spitzer, were turned in its direction. Well, naturally, the first, interstellar, from afar, an indisputable sensation. A new category of celestial objects even had to be created. They started with the letter I, interstellar. Shape. So we started tracking it. It turned out to vary in brightness, brighter, then dimmer, and it keeps repeating. We found out that the object was spinning, but still the brightness was changing too much. Pretty soon, it became clear that this was because of its shape. It's almost cigar-shaped, about 35 meters wide and up to 200 meters long. That's where we clutched our heads once again. There is no such asteroid among 1 million discovered asteroids in the solar system. Not a single one. Many people's first reaction was, OMG, what if it's an alien spaceship? Well, if aliens, then where from? Even if it's just an asteroid, still, where from? The trajectory was easy to trace, which was immediately done. All the data indicated that the space guest arrived from the constellation Lyra, and there was much evidence pointing to the star Vega, which, by the way, has a planetary system, but it is extremely doubtful that the object was lost exactly by the Vega system. If it travels, as assumed, for hundreds of millions of years, then Vega was in another part of the stellar sky. It should also be added here that the object was discovered rather late. That's because it was flying almost from the side of the sun. We still cannot detect such objects in the sun's side for quite understandable reasons. Any telescopes get blind. By the way, this is one of the rather acute problems in early detection of dangerous asteroids. That is why we noticed the Chelyabinsk meteorite on February 15, 2013, only when the shockwave was already at full strength, blowing out the windows in city high-rises. It also flew from the sun's side. So Oumuamua was discovered when it had already flown very close to the sun, inside the orbit of Mercury. This was already an anomaly because this zone is completely empty and none of our comets and asteroids fly there. and this one was literally flying almost straight towards the sun and circled it at a speed of about 90 kilometers per second. We should remind you that we have never seen such speeds in the solar system in our lifetime. And so, after circling the sun, it headed towards Earth, and we still didn't see it. The robot telescope detected the object only when it had already passed Earth and was beyond the orbit of the planet. And it could have crashed without warning, like the Przybylski meteorite. But this time, we were lucky. When the unusual long shape of the object was identified, even many skeptics, who had never believed in the existence of other intelligent civilizations, trembled. We decided that since it might be an alien ship, why don't we send it a radio signal? And we did send it. Unfortunately, or fortunately, we didn't get an answer. Then, after all, we decided to consider it as an object of natural origin, at least within the framework of scientific impartiality. But this impartiality was greatly shaken again in the course of further analysis of the data. Oumuamua managed to sweep inside Mercury's orbit, perform a gravitational maneuver under the sun's gravity, turn and accelerate, heading out of the solar system. Okay, again, what does accelerate mean? And that's just another mystery that added a significant portion of probability to the fact that this is something artificial after all. And it's even capable of speeding up like this. It looks quite logical. A ship flies, runs out of fuel, flies into the first star system it can find, flies close to the star so as not to melt, and to charge up as much as possible. Then gives gas and flies away. And that's exactly what it looked like. Many had to exercise wonders of restraint again so as not to be under any illusions about aliens. After all, engines can also be of natural origin. We see this all the time. Real jet propulsion is demonstrated by comets approaching the sun. But in this case, it was not so simple, which we are going to discuss below. Oumuamua flew away as quickly and swiftly as it had come into our solar system. We did not manage to explore it close by spacecraft, although there was such an idea. There was even an announcement of a feasibility study for a Starship probe mission to Oumuamua. It was developed by the Initiative for Interstellary Studies. The document was called Project Lyra. But after careful evaluation and comparing the possibilities with the risks, it was decided to abandon the idea. Maybe it was for the best. What if it really was an alien ship, and the crew there would consider our probes as a threat? Anyway, the Oumuamua flew away and left a lot of questions and mysteries in its wake. There's something about this whole story that is mind-boggling. We mentioned earlier that the anomalous, non-gravitational acceleration of the object after its approach to the sun could be caused by the same thrust effect which occurs in comets. One side is actively evaporating, creating a conditional pushing force. But there is a little detail here that ruins the whole idea. We did not notice any cometary activity in Oumuamua. As you remember, it was identified as a comet only at the first detection, and then reclassified as an asteroid just because of the lack of signs of cometary activity. Neither spectral gas lines nor dust was detected. How did it accelerate then? In the video, we talked a lot about the trajectory of the object already when it flew through our system. But its galactic trajectory looks not less, even much more interesting. The object appeared in the sky from the direction of the so-called solar apex. This is the direction in which the solar system in the galaxy moves in relation to the surrounding stars. It is located in the constellation Hercules, close to the constellation Lyra. This direction of Oumuamua's emergence suggests that it is more likely that it was not that it came to our system, but that the solar system came to it. Literally like a car on the road that hit a pebble, throwing it by the wheel on the roadside. And from this, we can assume that in relation to the solar system, the object was not quite stationary, but obviously lived its own life. How and why? Finally, no one neglected the fact that we have not ever seen such a shape among all previously observed asteroids and comets. And there are, let us remind you, more than 1 million of them. It was exactly cigar-shaped. Such a shape could still be explained by tidal pull, when the boulder was still forming in its native stellar system. But there is no less convincing data that the object has the shape of a flattened pancake, and no one has been able to explain this yet. There is an opinion that in order to solve the Fermi paradox, it is not necessary to find real aliens or a guaranteed proof of their existence. It would be enough to find something that we can't explain by natural origins. Oumuamua is probably the first contender to be this something. And here we return to where we started. Maybe we have never been so close to solving the mystery of whether we are alone in the universe. This time, the key has slipped away. But even the mere fact of such an encounter is a source of hope. It's unlikely we'll ever see the answer to this next mystery firsthand, but it is in this unknown that the universe's captivating enigma lies, driving our eternal quest toward the stars and the exploration of the boundless cosmos. The universe has existed for so long that its age is beyond our comprehension, and it will continue to exist for much, much longer, but not forever or forever. And if the universe ends, what happens then? That's a question humans have been wondering about ever since they learned to think, and we're still looking for an answer to it. Scientists already have several plausible hypotheses for the death of the universe. It could run under several scenarios, and some of them are truly overwhelming. It is what the death of the universe will be that directly determines what comes after it. Could the expansion of the universe rip it apart? What would happen if the universe begins to contract? Was the Big Bang the only one? And will it happen again? Today, we will answer these and other questions. What will happen after the universe dies? Please give this video a thumbs up. Likes are not just numbers. They send a signal to the YouTube algorithms that our content is valuable to viewers. And don't forget to subscribe. The earliest theory of the origin of our world is the so-called stationary universe, or steady-state universe. And the word origin is rather conventional here, because there is no origin. Supporters of this theory assert that the universe not only has no beginning and no end in space, but it also has no beginning and no end in time. They say it always has been and always will be. It has always been and always will be in a state of stable equilibrium. Even ancient people could easily come up with such a theory, because it is quite difficult to realize that something so huge, majestic, and incomprehensible as the universe can once come to an end. However, scientific data soon showed that this theory is most likely wrong, because it became clear that irreversible processes occur in the universe. Logic suggests that if something can end, then everything can end. Indeed, further physicists found out that at a deeper level, all processes are irreversible and everything tends to destruction. It is called entropy. And again, we make a speculative assumption. If it is clear that everything tends to destruction, it means that there was a moment of creation in the past. In the 1910s and 1920s, the Big Bang theory was formulated and became widely recognized. It is now one of the most stable scientific theories, and it helps explain the nature and evolution of the universe. But, as it often happens, only partially. It is pointless to ask modern scientists the question, what was there before the Big Bang? And today, we do not have such a goal. We are trying to deal with the opposite and find out what the end of the universe will be like. And we already have at least some background to make assumptions about it. You've heard many times that the universe is expanding, and it's doing so at an accelerating rate. This is really true, and a strange scientific term appeared in the late 1990s, dark energy. It is the cause and driver of this expansion. We call it dark energy not because it's actually dark, but because we don't know anything about it. Obscure energy would be more appropriate, but we don't even know if it's energy at all. But it's a convenient patch for a hole in scientific knowledge, and we'll use it like everybody else. So, there is something in our universe that is causing it to expand, and it's even more amazing how it all works. Yes, galaxies and clusters are flying apart, moving further and further away from each other. But this happens because space itself is expanding in all places at once. At any point in the universe, space is getting larger every moment, and this process is accelerating. And interestingly, all large objects are moving away from each other in all places at the same time. If you don't get it, here's a typical example with an ordinary balloon. If you draw small objects on it and then start inflating it, these objects will start moving away from each other all together at the same time. And this process has no center. If you imagine yourself on any planet in the universe, you will see that you are in the center of the universe, because everything is moving away from us in equal proportions. And wherever you move, from each of your new locations, you will see the same result. Everything is moving away from you in different directions, as if you were at the very center of the process. There is one very grim consequence of this, and it will lead to one of the ways in which the universe will perish. And you're about to find out what that catastrophic prediction is. What happens if we keep inflating our balloon? It will burst, obviously. And what happens if dark energy continues to inflate the universe? Well, it surely won't burst, you would say. Well, it may. It really may burst. And there's a very convincing theory of the Big Rip proving it. Look, here's the thing. We know that the farther away points are from each other initially, the faster they move away from each other. At some point, this speed starts to exceed the speed of light. Just in case, let us remind you once again that there is no violation of the laws of physics here, as it is not objects moving at such speeds, but space itself is expanding so rapidly. So the point where one object moves away from the other with the expanding space faster than the speed of light is the point of no return. It's called the event horizon. Anything that crosses that barrier relative to us ceases to exist. Just imagine. First, the most distant galaxies and clusters will disappear from the sky. Then, the stars of the Milky Way will fade, one by one. And finally, our sun will take its turn. At first, this process will be imperceptible, but then the effects will become more and more noticeable. If some poor soul is unlucky enough to be around to see it, he or she will see the sun suddenly snapping from an invisible tie and flying away to nowhere, leaving the earth in total darkness and complete loneliness. But this is only the first part of the final scene. Further, the process will go even more rapidly. The event horizon will quickly reach the Earth.
Oh, Jesus. Oh, my God!
It will be torn apart, and then, even faster, the invisible, insuperable boundary will already be the size of an atom. And in the end, all things will simply cease to exist in an instant. It's impossible to say what happens afterwards, because before and after are categories of time, and there will be no time after the Big Rip. Sure, it's a gloomy end that brings a heavy sense of hopelessness, but there is an equally likely alternative, much more optimistic. Today's observations show that space is expanding, and the rate of expansion is increasing. However, let us recall that we know nothing at all about the nature of dark energy. It may well have properties currently unknown to us that could reverse the expansion processes. So once again, just because space is expanding at an accelerated rate now doesn't mean that it always will. What happens to a balloon if you stop inflating it and leave it for a couple of days? It starts to deflate gradually. And here, oddly enough, everything can happen in a similar way, but with very different special effects. Yes, it's quite possible that the universe will sooner or later stop expanding and start compressing. This could happen if the total gravity generated by all the matter in the universe exceeds the force of its expansion. This scenario is known as the Big Crunch. In this case, the processes in the universe will run their course until its size is reduced by a factor of 5. Clusters of galaxies will unite into one supercluster, which in fact will fill the entire universe, much shrunken by that point. Thus, such processes as birth and death of stars and formation of planets will continue to occur inside galaxies. But that'll be up to a certain time. As the universe contracts, it will become denser and hotter. When the universe contracts by a factor of 20, its volume will be only 1% of its current volume, and all galaxies will merge into one. The temperature of the cosmic microwave background will be 274 degrees Kelvin by then, and will continue to rise. That means there will be no liquid water left in the universe. It simply won't be able to exist. And this would mean the end of existence for biological life as we know it. Further compression of space will cause the universe to heat up even more. The planets will melt. All matter will crumple into a huge cloud of boiling plasma. Then, atoms and subatomic particles will scatter, and eventually, the universe will collapse into a singularity like the one at its birth. And that's it? The death of the universe? Again, we don't know. We can only speculate and construct conceptual experiments. And such speculation has led physicists and cosmologists to a very optimistic theory. It is known as the Big Bounce theory. According to it, when the universe reaches a singularity after the Big Crunch, it will be reborn by another Big Bang, and the cycle will be repeated over and over again, presumably forever, as far as we can talk about eternity in the absence of time and space. And there's not even much to add here, because we see the consequences of at least one Big Bang all around us. Although, who knows what the next universe after the Big Bounce will be like? Maybe there will be different laws of physics. Not to put too fine a point on it. We don't know if there will be any physics there at all, or if something completely beyond our comprehension will be going on there. All the described scenarios are interesting, appealing, even funny at times. But there is one scenario that seems the most likely to scientists. And it is, as usual, the most boring, although very dramatic. This is the heat death of the universe. The point is that the universe may or may not expand further, but in any case, entropy is occurring in the universe. Everything collapses, energy is dissipating, and everything is moving into chaos anyway. And unless the previously considered scenarios happen, the universe will just slowly fade away. So how is that going to happen? There are 4 clearly defined epochs in cosmology, each associated with a particular phenomenon. We live in a so-called stelliferous era. There is a lot of interstellar gas in the parts of the universe around us. It serves as the raw material for star formation. New stars are born from this gas, and this process will continue until all the interstellar gas is depleted. The end of this epoch is expected to occur between 1 and 100 trillion years from now. By then, the Sun and the vast majority of other stars will have exhausted their nuclear fuel and become white dwarfs, neutron stars, or black holes. The next epoch is known as the degenerate era. There will be no more main sequence stars. Most of the matter in the universe will remain as white and brown dwarfs, and some will remain as neutron stars and black holes. It will take an enormous amount of time, about a duodecillion, or 10 to the power of 39 years, for all these objects to cool down. White dwarfs will gradually give up their heat in the form of radiation and turn into black dwarfs. As for brown dwarfs, they too will cool down. The thermonuclear reactions occurring on their interior at a sluggish rate will eventually cease completely. At this stage of the universe's evolution, the main processes will be the annihilation of dark matter and proton decay. The proton is the elementary particle from which atoms are built. It's the smallest brick of matter. It is considered one of the longest living elementary particles. Its lifespan is about 100 duodecillion, or 10 to the power of 41 years. Now, by the time this era ends, matter in the universe will look like a vast ocean of free-floating elementary particles, with the occasional neutron star or black holes among them. The next era is the black hole era. According to some theories, black holes will form clusters and eventually merge together to form one giant black hole. According to alternative theories, black holes will slowly evaporate before disappearing completely. Black hole evaporation is a quantum effect caused by so-called Hawking radiation. The smaller the black hole, the more intense its evaporation, which eventually strips the hole of all its matter and energy. This process is expected to continue for 10 to the power of 100 years, a number also called a googol. Anyway, eventually, there will be only lifeless space left in the universe. This space will contain only tiny fragments of the former world: photons, electrons, positrons, neutrinos, and quarks. Over an unimaginable amount of time, these tiny fragments will occasionally find each other in the dark, empty universe. The collision of electrons and positrons will cause them to annihilate. In such a state, the universe could exist virtually forever.